some reason.
స్టార్ట్ అవుతున్నా నేను మీకా
నాకు ఇంకా స్ట్రీమ్ రావట్లేదు.
స్టార్ట్ అయింది సార్, ఎప్పుడు స్టార్ట్ అయింది లైవ్.
అచ్చా అచ్చా.
ఓకే,
Dr. Prasad?
సార్ గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
Good morning, Tej. Yeah, good.
మార్నింగ్ సార్.
Yeah, very good.
యా.
Everything went off okay?
How are you, sir?
yesterday?
Yeah, went off well, sir.
Very good.
Okay, yesterday went on well, very informative lecture. Today we hope that it would be more interesting. Start discussing experimental model analysis. Seems. Schedule.
So yesterday we gave a problem solving session, sir, and there was a sort of I went through some of the MATLAB codes I had written in 2002, and I was trying to go through latest SimScape for doing lumped parameter systems modeling.
Mhm.
And so it was quite interesting to see the students were quite interested in all that.
So total participants is what? 50? How many?
Yeah, nearing 50, sir. 45 plus.
Oh, that's pretty good, right?
Yeah, yes, sir.
Oh yeah, that's very good actually. There's been a lot of interest, and there were many more people wanting to join this thing, but it was too late for them to
Okay.
register through the portal, I guess. Quite a
And
turnout.
again, because I'm not familiar with this and Zoom, I may forget to share screen and all that. Please warn me, okay?
Yes, sir.
Okay, sir. Okay.
Like
Yeah.
yesterday.
Dr. Ravi Prasad, there is some setting wherein the beeping sound which is created by people joining in can be muted.
Yeah, that way you can do.
Yes.
Participant, hello. Mute entry, mute on entry. Okay.
Not only that, that signal which comes, that beep.
That beep only, mute on entry. That is, when they are entering, no sound will come.
Okay. Oh, it's coming. Still coming.
Entry and exit tone. Okay, that okay.
Entry exit tone.
Right. Yeah, we have to wait. Maybe people are joining till so 8 o'clock. Maybe too early here, bit.
So you got refreshed yesterday, sir? After today, yeah, today.
I'm fine. Today was over here the last day, but I did not go to the office.
Yeah.
We're trying to get a virtual get together somehow.
I see.
We're
So
not in a
they're
complete
having a
lockdown,
farewell.
but still, too many cases going around, So.
Yes, sir. So one of my students, Harika, is also here. She's working on Lamb wave propagation in composite plates.
Oh.
Yes. And
She graduated right now with you? Or
no, she's in her first year now.
Okay.
The person you're talking about is Priyanka. You met her.
Yes, yes, I thought I.
She's about to graduate. She's
Okay.
finished her requirements. She's about to graduate.
Did you go to IIC Bangalore?
Sir?
You're supposed to have a trip to on this 23rd or 24th to IISc Bangalore, no? Did you go?
No, sir. Actually, I'm not traveling anymore.
Okay. We finally got the shock tube, okay, the small one for 70,000, 68,000, and
Oh yeah, Professor KPJ Reddy's firm.
yes, yes, Shruti's technology is very good. It's working very, very well, very
Yeah.
fast, very quick turnaround in sample testing. I'll be talking around about it in my, research on day 5. So
Right, right.
instead of taking at least half a day for setting up in the big tube, this is much faster.
Yeah, that was a big exercise. I
Mhm.
remember turning those nut bolts and the process. Every time we press the button, we used to be sweating. Uh,
Mm.
I remember that. Whether it will go off or not. Uh,
Yeah.
Fun times.
This is much more. They don't use a burst diaphragm. They use a valve. Quick
Oh,
release valve.
okay.
Quick release valve. Very very efficient. Very very effective. So
I
Matt
see.
Lowe is trying to convert our old system to this sort of a quick release design. So
I see.
because this
Matt is the
diaphragm,
new.
yeah, diaphragm bursting is unpredictable. See.
Yeah, yes, sir. So the repeatability is quite good. And,
Oh, very good. Very very
okay,
good.
okay.
But I think we have to run it with the liquid nitrogen. For
Oh,
maintaining that. Yes. Use the
I
same
see.
one we use for our SEM and all that, same tank, same this thing. So.
Okay, okay.
And up to 500 psi maximum.
Oh, okay.
Yeah, yeah, limitation. That's okay.
Limited.
That's most of our
That's fine.
samples are yeah,
Yeah.
works.
For
We really
most,
want to go for a bigger sample, we go to the other tube, but otherwise we use this one.
yes.
And all the students are able to get their hands on. It's now located in the where Dr. Lackey's pultrusion lab is there. Pultrusion is
Oh,
removed,
yeah.
taken away completely,
Okay.
and replaced with this setup,
I see.
and other equipment in that for undergraduate research.
I see. I see.
It was justified based on saying that undergraduates will get their hands-on experience and get trained to go to ERDC and all that. So they agreed for
Yeah.
it to get from the funds that we had on the grant to buy this
Okay.
equipment. So it worked
Okay.
out very good. It was a good investment.
Yes, sir. I would love to see that sometime.
Mm.
We'll start in another.
So it's 8:04.
Okay, sir. We'll wait for a couple of minutes and then we'll start. People may join because a bit early people are being here. Okay.
Um, Meanwhile, can I ask the participants to, come forward to introduce themselves, those who have not yet done so?
Okay.
How do you keep track of the attendance and all that? Just via this portal?
Screenshot, sir. Yeah, attendance portal also
Screenshot.
we have to confirm, sir. But here we are taking screenshot.
Screenshot.
I'll call upon my Harika. Can you introduce yourself?
Yes, sir.
What you
Am I
are
audible,
doing
sir?
to everyone? Yeah.
Yes, sir. Good morning, sir. Good morning, everyone. Myself Harika, I'm working under Tezeswi sir. Actually, I have completed MTech last year, 1 year back, and I've joined as a JRF under Tezeswi sir for the Imprint 2 project, which is condition assessment of composite panels. In the same way, we are continuing the project as a PhD thing by extending some work. Experimental work is going on now, and we are planning to do this simulation presently. Yes, sir. This is
So the plane waves and all that, that's all theoretical or any experimental model, experimental one?
sir. Actually, signal processing is going on in the factories. We are planning to do this in analytical, like Abacus software. Using Abacus software, we are planning to do the simulations. And
So this is
also, we
under
are
the
thinking of a
imprint.
theoretical validation also.
So this is under the imprint project, sir, and we have an industry collaborator with us,
Mm-hmm.
and they are the ones who are manufacturing the panels and also embedding the sensors during manufacture.
Okay.
And they are providing us the experimental data based on their because the quality control and all this thing is integrated within their manufacturing cycle.
Mm-hmm.
So the measurement, the data acquisition, and all that has to be on site for their at factory. So they do the experiments, and sometimes from time to time we go and join and see what is you know if there is any requirement. And
Where is it located?
basically,
Close
this
by
is in
or?
Hyderabad. Hyderabad.
Oh, okay.
Hyderabad. So basically, Harika has also done some lamb wave experiments when she visited there,
Oh,
and
okay.
her primary focus is on the computational aspects.
Sir, can we start? People will join slowly, like that. Okay.
Shall I share my
We are running
screen?
short of time.
Yeah.
Yeah.
Share my screen, Tej?
Yeah, yes, sir. Yes.
Yeah,
Yeah,
please,
let
sir.
me
Please
know
go
if
ahead.
it doesn't show up,
Yes.
okay? You got to warn me, okay?
Yes, sir. Yeah.
Yeah. Good morning, all of you. The day 2 session starts with introduction to experimental model analysis, applications, advantages and limitations, frequency response function and transfer functions, followed by FRF measurements, test system configurations, supporting the structure and exciting the structure, and then discussion about model analysis using impact hammer and its test setup, data measurement of model parameters and model acquisition, and obtaining frequency response function and extraction of dynamic parameters. These are the things Professor Manthan is going to cover, and followed by laboratory demo will be there. So now I invite Professor Mantana to start his lecture. Thank you.
Okay, thank you. Can you see my full screen?
Yes, sir. Yes.
Okay, full mode screen. Okay. All right. Good morning to all of you. It's night time here, 8:30, and I'm still fresh. To follow up today from last lecture, the key terms that we'll be repeatedly using are frequency, damping, and motion associated with each mode of vibration of a structure. So these three things, what they mean, how to go around getting them and all that through the both analytical and experimental modal analysis techniques is what we'll be talking about today, and tying the two together, the analytical part with the experimental part, and then moving on with the experimentation and techniques and all that. Again, I want to acknowledge the articles and material provided by Peter Avitable and Hibler's Engineering Mechanics is an undergraduate textbook we use, which already covered for the fundamentals, and material from these various sources where I had the opportunity to be, attended seminars, training sessions, and all that. And to my PhD student, Mr. Suman Babu, who came for his help in all this. So analytical and experimental, how the two are tied up, okay? Before we jump on to the actual experimental part, we have the single degree, we started off with the single degree of freedom lumped mass system, for which the equation of motion turned out to be mass times inertial force, which results acceleration inertial force, the so-called dissipative force, and the spring times the displacement, the restoring force, all of them equal to the external force. All these are equal to each other. When you form a solution for this sort of equation, you get two forms. One is called the initial transient condition, meaning that essentially if you suddenly apply force to a spring mass system, the sudden movement and all that will create a transient response, which will decay out initially, based because of a damper. So the transient, the sudden jump based on the sudden application of the force will die out, and it's all based on the initial condition. Very sudden high transient force dying out, and then it will be followed by the particular solution part, which will depend upon whatever the conditions of that forcing function are. The initial force part, the magnitude, creates the transient function, transient, and then the oscillating condition of this forcing function, whatever it is, will be dictated by this particular solution. So that's the mathematical representation of this whole single degree of freedom system. Now we keep hearing, you may be hearing terms like transfer function, frequency response function, things like that. What are they? What do they mean? And this gives a description of this, how they are related. From the time domain, the physical domain that we do the testing, you can mathematically transform it into the so-called Laplace domain. S parameter is used, or the frequency domain. Okay, either one. Transformation of the time domain into this, from Laplace you can go to frequency, from frequency back, and all these are all different ways of expressing the same quantity in different forms for different purposes. Laplace domain is very commonly used, Laplace parameters and all that. So what are the relationships? Let's take a look at that before we move on, okay? For a single degree of freedom in the time domain, if this is there, using the parameter S, you can substitute that and transform this into the Laplace domain defined by these quantities, where S is equal to a sigma plus j omega, imaginary quantity, real and imaginary part. This same thing, if you want to get in the frequency domain, from the Laplace to the frequency, you simply substitute the omega, okay? Instead of S, substitute j omega in these terms, and it will be called as in the frequency domain. Omega is radians per second, it's frequency. S is the Laplace parameter. So these are all this way substitutions. And if you want to see the Laplace domain, will have a standard solutions are there for in the Laplace domain, where you can set up the equation, Laplace domain representation of the system response, Laplace domain representation of the forcing function, and the so-called transfer function is the ratio of the output response to the input force, which can be expressed by this form in this fashion. So that transfer function as a function of S is a complex valued function which appears as a surface in the Laplace domain. What is that surface? You see this over here, very well pictorially depicted over there. The transfer function, and this is all the so-called, Laplace domain. All these are parameters associated with the Laplace domain, where it consists of sigma and j omega. Sigma plus j omega or sigma minus j omega, all these plus sigma minus sigma, it's a total domain of that form formed over there. Now, if you evaluate that Laplace domain, substitute for the S j omega, If you evaluate that function only along this axis, you see that this cutoff over here, only along the omega axis, a part of it, then it is the Fourier domain, Fourier transform. Laplace domain completely in the S parameter consisting of sigma plus j omega or a minus j omega and all that. And this function evaluated along the omega axis, radians per second, radians Fourier. That's called the Fourier domain representation. And that's what you'll see is the frequency response function. This is the transfer function. This is the frequency response, frequency, time response like this, frequency response along the frequency axis and things like that. So this Laplace domain data will have a magnitude, which will have a real part, an imaginary part, and a phase. S plane, it's a plane, a sort of imaginary S plane and a mathematical representation of Laplace parameters. Okay, that's how we tie it up. That brings us to this, what we look at practically using a frequency domain analysis, using a spectrum analyzer. This is what you're seeing. You don't see the negative part, but it's there. It's a solution consists of the negative part of the omega and a positive part of the omega. But this is what it really shows. This is the total roots and all that. So just to give you a tie-up of all these. So when you do the transfer function analysis, the ratio of HS is this over there. And each solution is called a pole for it. Pole 1, pole 2, like this is a pole, this is a pole, okay? Solution for the pole. Pole 1, pole 2, minus zeta, plus or minus square root of this is solution. Mathematically, this is what you do is a transform function where all these have meaning. Omega n in natural frequency and that C critical, okay, 2n omega n or 2 root k, and zeta is C over C critical, damping ratio. All these are there in the transfer function in the so-called S domain. Similar things will be there in the frequency domain. If you do this, the so-called plot, the pole location over here, this pole over here. If you do it, see it in the two-dimensional plane like that, the solution, the pole location, the transfer function goes to infinity at this point. See, transfer function goes to infinity at this point. That's the location of the so-called pole. And the conjugate, because it's a complex function. It'll be complex conjugates and all that are there. Again, it's a mathematical part of the S plane. And again, these quantities are all described over there for that part over there in the S plane. And there are other parts, the real part, the imaginary part, the log, magnitude. Sometimes it's described as a Nyquist plot, sometimes called a Nichols plot. Old days they used to use that. But most common plots are this, which we use for our work in the frequency, alternative forms of the frequency function. This is the books which will use phase verification. Log magnitude is what your spectrum analyzer shows you. It has two components, square root of real square and imaginary square is the magnitude, right? So these are the things we'll come across. Again, transfer function, some more math part of it breaking up into its pole P2 is equal to P2 star, and again, not to bore you with all this, but the solutions for this and all that are given over here. And if you add more and more systems, then time domain motion is described like that. Then you form matrices like we talked about yesterday. Okay, mass matrix, a damping matrix, and a stiffness matrix. And again, you can do all that analysis in the Laplace domain for all those mass and stiffness and matrix, where you come out with system matrices, and you can express the response as a function of the transfer function matrix multiplied by the forcing function, and is in adjoint of this. Then you Laplace domain, wherever S is there means you're in the Laplace domain. If you replace S with the j omega, you're going to come to the so-called frequency domain analysis. So formulating all these and element and expressing, you get an expression where it constitutes of what's called residue, which is important for our work. The residue is what will be coming into the mode shape. Residues are going to contribute to our mode shape. Okay, and then determined by the structural properties, and the pk, the p is the pole location, is a global property. A residue will be a local property associated with that particular mode, and this part, is a global property, like what is the frequency and all that. Again, you can express the transfer function in partial fraction forms, consisting of this matrix of all the residues. If you form all of these, then they consist of enough information where the complex residue in terms of modal vectors, okay, and each residue, and along the row, along the column, and all that, those vectors put together will create the so-called mode shape, modal pattern at a particular frequency. For example, for a 2 degree of freedom system, this and this, the total S for a particular this thing, the total response will consist of, for mode 1, mode 2, for the 2 degree of freedom, so put together. Okay, Q has been a set of equal to 1, which is arbitrary. Modes are normalized to arbitrary, normalized to a value called 1, because you're trying to look at what's called relative moments as opposed to actual moments, which can be obtained back if you input back the type of transducers, calibration factor, and all that. You can, but that's not as important in modal analysis as how relatively, with respect in a mode shape, each position is moving. That's one of the, maybe you can say, disadvantage or advantage, whatever it is. It's more important to know what the modal pattern is relative to each point rather than the actual values in a modal analysis experiment. Okay. And transfer function, again, some more things to talk about, modal testing implications. Modal parameters can be identified. This is a very key important thing, either one row or one column. Any one of them will give the modal parameter. We'll see pretty soon what they are. What are the assumptions? Dynamics described by linear second order differential equations. Structure exhibits symmetry, or so-called reciprocity. That's extremely important. I'll emphasize it more in the later lectures. What is the concept of reciprocity? Now, only one mode exists at each particular pole, and modes are defined in a so-called global sense. When we do these measurements, we'll come across a term called a driving point frequency response function and a cross frequency response function. The driving point measurement is defined as a measurement where the response degree of freedom, location, and direction is same as the excitation degree of freedom. Meaning, at some point when you're doing a modal analysis, tapping a hammer and keeping an accelerometer at one point and tapping all around, at one point you have to touch the point where the accelerometer is, right? So when you're directly impacting at that point, that's given a unique name called a driving point frequency response function. That's got a lot of important data, whereas all other points of impact are cross functions. Okay, so this has got important things which we'll elaborate later. At a response at this, or an input at this, measured driving point frequency response function, residue for the kth mode, the residue which is a part of the mode, each vector quantity over there, pole location, component of the mode shape at degree of freedom. Again, we'll elaborate each one of these. Again, this shows pictorially. This is an important parameter for a driving point measurement. We notice that in a driving point measurement, all the modes peaks will be either peak, resonance, anti-resonance, resonance, anti-resonance, resonance for 3 degrees of freedom up to 3 mode shapes. So one important thing, if it's a driving point measurement, you should see on your spectrum analyzers resonances, anti-resonances, resonances, anti-resonances, and these imaginary components. This will always be positive point out with a negative this thing dip over there. And this is the phase which goes phase 0 to 180 cross at 90. then for the next one, all these phase, all these things are a typical output for a driving point measurement. Then this is also Nyquist plot. You'll get mode 1, mode 2, mode 3, like that. All those things will be there. The same data, when you plot real versus imaginary, that's called a Nyquist plot. And sometimes spectrum analyzers make use of this sort of a configuration to easily compute the so-called band, half power bandwidth and all that, rather than use this other technique that I use for my research to drop down 3 dB and all that. We'll talk about that later. But computationally, it's more efficient to get all the parameters regarding the maximum frequency at the point and the damping and all that using Nyquist plots computationally. It's much easier for the computationally to do this. So Nyquist plot is an important parameter for the purposes of spectral analysis from that perspective. Okay, I would rather prefer using this sort of a data computationally to get the data I'm interested in. But that's there. That's it. And sometimes there'll be more, each imaginary, coupled very close modes and all that. If you see like that, it consists of first mode, a second mode, a third mode, close put together jointly will be like that. Okay, in experimental modal analysis, the curve fitting techniques take into account zooming on to this portion and curve fitting this, zooming on to this portion and curve fitting this, zooming on to this portion, curve fitting this, for the purposes of getting the mode shape and other data. But really, the overall spectrum will consist of a little bit portion of each one of them. See that? When it shows up. These are closely coupled modes. They are like that. Otherwise, they are really distinct and this thing. Now, the other tests, all other data obtained by impacting some other point and picking up the response at the same time, any other points, are called cross-frequency response measurements, described mathematically as this cross function. Impacted 7 with a response at this point, picked up over here. That's the way, that's described. Again, all others are pole location and components. These components of this are the components of the mode shapes and all that and everything. So again, how that would look is shown in these pictures over here. How a cross function would look and all that. You see, any other data, log magnitude is always peaks. Peak, peak, peak. There's no anti-resonance. There's no anti-resonance. Anti-resonances will occur in the log magnitude plot only if it's a driving point measurement. We'll be dealing with it. Talk about it more and more. Okay. So again, the Nyquist plot for this will look like that. Cross FRF measurements will look something like that. Imaginary part and log magnitude and all that. So having covered that, trying to give you a tie-up between the what's called a transfer function and they are very, very loosely used. In when doing modal analysis, people suddenly say transfer function, or more realistically and clearly the frequency response function, but they are meaning one and the same. But really, each one is talking in a different domain, the so-called domain of the Laplace transforms and the Fourier transform. The Fourier transforms are all what lead to the so-called frequency response function because they come from the Fourier series, Fourier analysis, Fourier transform, for fast Fourier transform. So they're all related to the frequency response function along the frequency axis. Whereas realistically, transfer function term should be used more to the Laplace domain, the so-called mathematical way of formulating that in the Laplace domain. So most structures vibrate. So in operation, all machines, vehicles, and buildings are subjected to dynamic forces which cause vibrations. Very often, the vibrations have to be investigated either because they cause an immediate problem or because the structure has to be cleared to standards or test specification. Both possibilities. Whatever the reason, we need to quantify the structural response in some way so that its implication on factors such as performance, fatigue can be evaluated. And the way to do that is signal analysis techniques. By using them, we can measure vibration in the operating structure and do a frequency analysis. Frequency spectrum description, how the vibration level varies with frequency, can be checked against certain specifications. If you are in this business of performance and things like that, the result will be product of the structural response in the spectrum of an unknown excitation force. It will give little or no information about the characteristics of the structure itself. If you need to know more about the characteristics of the structure, an alternative approach is the system analysis technique, in which you need at least at a bare minimum, a dual channel FFT analyzer. Does it mean that that's it? No, you have spectrum analyzers with a lot more, 4 channel, 6 channel, 8 channel, and all that, for getting what is called multi-input, multi-output. When you want a single input, single output, is a dual channel with 2 channels. FFT, fast Fourier transform analyzer, can be used to measure the ratio of the response to a measured input force. One channel of that analyzer will have the response transducer input, one channel will have the force transducer data coming in, and once you do the exercise, these two are manipulated to get the ratio of the response to the input force, which is nothing but the frequency response function. The frequency response function measurement removes the force spectrum from the data and describes the inherent structural response between the various measurement points. From when you go get a set of FRM measurements made at defined points on a structure, which you initially define. You can identify and define, this is what, like a finite element. What do? You're breaking up into elements and defining them and getting the data, feeding in. That's on a computer. Here on an actual structure, you discretize the structure, make some points, and number them and feed that data to your software too, so that it can reproduce what's going on. Give it a file name and all that. We'll see all that later. So, and you can get a set of measurements made at defined points. We can begin to build up a picture of its response. The technique used to do this, the whole process is called modal analysis. So at a bare minimum, you need a dual channel analyzer so that you get an input, you get an output. And the ratio of the output to the input force, whatever type of force is gained, whatever type of response, the ratio of it manipulated through the FFT analysis very fast, very quick, using the Fourier transform analysis, will give you the so-called frequency response function, which has the data which you're looking for modal analysis. What are they again? The frequency at that particular part, the damping associated with it, which can be obtained from the so-called half power bandwidth, and each component, each part will be a part. The residue of that will give you building up data for the modal shape pattern. So frequency response function. Again, all structures exhibit modal behavior. Okay. An FRM measurement made on any structure will show its response to be a series of peaks. The individual peaks are often sharp with identifiable center frequencies indicated that they are called resonances. What is a resonance? When the forcing frequency matches the natural frequency of that structure, it is a resonant condition, which is in a way a weakness. It's the weakest link. That resonant condition is the weakness of the structure. Because if you force something at that and keep it at that point, the structure will break. So it's a weakness in a way. Resonances, each typical of the response of a single, as if it's a response of a single degree of freedom. If the broader peaks and all the peaks are analyzed, 1, 2, 3, or 4, whatever you can capture within a frequency range of your spectrum analyzer, which you can set, whatever range, are analyzed with increased frequency resolution, 2 or more resonances are usually found close together. The implication is that a structure behaves as if it is a set of single degree of freedom substructures. This is the basis of modal analysis, through which the behavior of a structure can be analyzed by identifying and evaluating all the resonances or so-called mode, each resonance is associated with a mode in its response. Let's begin with a review of how structural response can be represented in different domains. We talked about it, okay? In the physical domain, the complex geometrical deflection pattern of the bell, for as an illustration, is taking a bell, okay, and exciting it. And what do you see when you see this excitation on that bell, okay? In the physical domain, you'll see something like this, okay, with the excitation, okay? But if you break it up and in the time frequency response domain, you'll see that there are some spikes and then something like this, something like that, some, these peaks, peak, 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 peak. Well, each one of those peaks is associated with a particular modal pattern. You can separate this. You can do the frequency frequency domain analysis and break it up each and see that if this is if we are able to excite that bell at that frequency, this is the mode shape of that pattern. Then the second frequency in the time domain will consist of this sort of a response decaying. All of them are decaying. Okay. This is the modal pattern associated. And if the third mode, all these, you see. So the total domain physical response consists of a combination of each one, mode 1, mode 2, mode 3, mode 4, and much, much more, which are higher modes. Always in frequency analysis, as you go to higher and higher, the quantities becoming smaller and smaller. The most dangerous frequencies are the fundamental, either fundamental bending or fundamental twisting or fundamental any other. The fundamental modes, shearing, the fundamental 1, 2, they are the most dangerous ones because the amplitudes are large. So the overall frequency response function of the bell in the time domain, in the frequency domain of the sine dual gives a spectrum containing a series of peaks shown. In the modal domain, we see the response of the bell as a modal model constructed from a set. You can take that and construct this as the modal domain. You see that? Overall consisting of spring mass damper and spring mass damper combinations. You can build it up to represent that. Will consist of as if the whole total modal mass, that's why it's called modal, is normalized to modal mass, is going at the first frequency with this damping factor, this one. The second total modal mass is unit mass, unit normalized, that's what they call it. That's the way they mathematically they do the analysis, and each one, which consists of a mode here and mode here, all combined together is the general thing that you talk about. Looking back from modal domain along the rows in the illustration, we see that each single degree of model is associated with a frequency, a damping, and a mode shape. These are the modal parameters. This is the damping. This is the damping. Frequency is associated. What are frequency? Omega first frequency, second frequency. Omega is the frequency. And curve fitting those frequencies as you go along will give a modal pattern, which we'll see a mode shape, which together form a complete description of the inherent dynamic characteristics of the bell and are constant whether they are ringing or not. They are inherent within the structure. Okay, it is just that when you excite it in a general pattern, if you somehow are able to excite this bell in its frequency, first frequency, only the dominant one, the first one will show up. Go on. If you're somehow able to excite it at a frequency associated with that at the second frequency, this fellow will be dominant. Third one, so on and so on. A general disturbance of this bell or any other structure which you see when you disturb is a combination, simply of a combination of its various natural frequencies put together. So here let's close it. Modal analysis is the process. What you're trying to do is the process of determining the modal parameters of a structure for all modes in the frequency range of interest. You have to select those, okay? The ultimate goal is to use these parameters to construct a so-called modal model of the response. Two observations worth noting here are that any forced dynamic deflection of a structure can be represented as the weighted sum of its mode shapes. Each mode can be represented by a so-called single degree of freedom model. It totally combined, each one is built up of a single degree of freedom model and all that. Again, going back to what we did, repetition of some of that in a different form. A single degree of freedom consists of this and mass stiffness damper. We did this before, so I won't spend more time, and mode location and all that. The residue of a decrum is an imaginary number which expresses the so-called strength of that mode. Okay, the residue part of it gives an indication of the strength. Let's dwell a little bit on that residue, because it's got something to do with the modal pattern and all that. As indicated in the illustration, both the pole location and the residue can be obtained from the measurements made on a displayed frequency response function. The modal parameter model thus gives the relationship between analytical models and experimental measurement. Let's take a closer look at pole location and residue. As an example, let's take a turntable, which is modeled as consisting of 1 kg, and a damper whose units are Newton meters per second, okay, Newton meters per second, and a spring 400 newtons per meter. These are the physical characteristics of this table. Let's take a car, a 1000 kg car with a damper of 8000 newtons, 400 of these characteristics. If you calculate the natural frequency of this in radians per second, it's 20. The natural frequency of this also is 20. The damping sigma, C over T, I'm critical and all that, the damping ratio sigma is 4. There's also 4 here. The dampened natural frequency, it's called omega square minus that sigma. This dampened natural frequency is the slightly smaller than the natural frequency. And the so-called residue combination for all this is different for this as opposed to this. Okay, so that's the difference. The response. The pole location contains of two modal parameters listed. The real part of the pole is the rate at which the vibrations die out, related to modal damping, and the imaginary part is the frequency. For each pole, remember sigma plus j omega modal frequency. This information is held in the form of a center frequency and a half bandwidth at a minus TB reference. So half bandwidth. Why that half bandwidth comes is more from analogy of electrical circuits and all that. Most of the energy within the spectrum is at the so-called half power point, half power bandwidth. Is 3 dB decibels down from the peak, or if it's a linear scale, 0.707 from the bottom. Okay, at that point, the energy content is that half power point. That's why that's used for the purposes of damping and all that. The pole location describes the shape of the magnitude and phase curves of the FRF. The residue is a mathematical concept and has no direct interpretation in physical terms. It carries the absolute scaling of the FRF and the level of the magnitude curve. We'll see later that the residue is related to the third parameter called mode shape. We make use of that residues to build up the vector consisting of the mode shapes put together. So the residues play a role. It's a mathematical concept, but it plays a role in building that so-called mode shape for the structure. Residue is also sometimes called a pole strength, but the magnitude of a mode is not given by the residue alone. It consists of that residue divided by that sigma. The illustration gives an example of the properties of a pole location residue in a simplistic form. A hi-fi turntable unit could have the same stiffness, same damping, same mass distribution in a car, and hence the same pole location, okay, roots and all that, equation omega d and all that. The measured FRFs would have the same shape, frequency response function of this and frequency response of function of this is the same, but the difference is response to unit force would be quite different. The difference can be seen in the residues. We take this is for this fellow, and this is for this fellow, the response over here. And the way the decay rate is same, remember, zeta is the same, so they'll decay and all that. but the residues will be different for this response to this response. That's just to give you for that single degree of freedom system. But we make use of this at each impact and response, impact and response, impact and response all over, and build these together into a waterfall pattern and create the so-called mode shape. That's what mode shape part, the third part is. Again, multiple degree of freedom models. That was a single degree of freedom. A degree of freedom, by definition now, is a measurement point and direction defined on a structure. Now we got to be careful. A rigid body mode has three, I, J, K components. Okay, all says and response also can have a I, J, K possible. So we have to give some sort of a keep track of all these as we go along. So we'll keep track of it by an index. Index is used to indicate the response degree of freedom, response I, and J is the excitation degree of freedom, I and J. Additional indices X, Y, and Z may be used to indicate the direction also. Okay, I, J, K, you can impact it this way. You can impact it directly in the perpendicular to the plate, or impact X, Y, G coordinates at each point. Oh, multi-degree, multi outputs, multi inputs, all possibilities, but typically, mostly, accelerometers are designed to pick up the response in one direction, like this, if you look at that. But there are what are called triaxial accelerometers. They're triaxial accelerometers. If you excite the structure anywhere like a hammer, it will pick up inside are built-in piezoelectric sensors which will build up this vibration, one coming out of the plate and the other Z direction. All three will be picked up instantaneously. Some analysis require you to have accelerometers, then also excite in three direction. Though we can make it as complicated as possible, And again, it's all curve fitting, keeping track of the data and all that, and curve fitting. Let's take the simpler cases of this. Response I, input J. Is that clear? So the frequency, the so-called writing the Hij omega in the form in two different ways, we obtain the two multi-degree of freedom models shown as equations in this illustration. Okay, so you break up Hij, response response at I due to input at the point J. Force input is J. You see that? Response at I. The MDF FRF model has the sum of single degree of freedoms model for one each mode with the frequency. So continuation is the summation of all these at I is equal to 1, 2, 3, or whatever these quantities are. This is summation is 1, 2, 3, which is a combination of first, second, and third. The modal parameters defines in terms of the pole location. Modal frequency and damping are global properties. The residue is a local property, which gives the mode shape, relates to a particular combination of degrees in particular mode. So we have started off our very first exercise of what is an impact where and what is the response for building up our experimental modal analysis. Well, is that the only way? No. You can keep a shaker here instead of a hammer and move the accelerometer to different spots. Okay? Response can be put with a single input shaker. Whereas impact hammer, more common, response accelerometer is fixed and the hammer is roving hammer. It hit various parts and get data. All this, we'll refine all this. We'll refine all this. Dave, how are we doing for time?
So we are doing good, sir.
Hello?
We taking a short break, sir, at 8:55.
What is the time now? I don't know.
8:49, sir. Another 5-6 minutes we'll be taking.
Yeah, I'll finish this then. Okay, all right. Just warn me about it. Okay, all right.
Yeah.
Now, I told you the important. This is it. In response, input response. And from now on, we'll be talking about this all the time. Impact here, response there, or impact here, response here. You see that? If I go, and impact, normally it's not done right on the accelerometer. You don't want to destroy it. But if the impact is done at the same point on the opposite dial, that's called the driving point. Remember the driving point response at I due to input at I itself. at that point. That's an important parameter, driving point measurement. Now, what is a mode shape? How is it generated? A mode shape is, as we said in the Bell example previously, a deflection pattern associated with a particular modal frequency or a pole location. A pole means a frequency associated with that. It is neither tangible nor easy to observe. It is an abstract mathematical parameter which defines a deflection pattern as if that mode existed in isolation from all others in the structure at a particular instant of time. The actual physical displacement at any point will always be a combination of all the mode shapes of the structure. With harmonic excitation close to a modal frequency, suppose instead of giving us, this is also called broadband excitation, by impacting, you're creating a direct data function in the time domain, which equivalent in the frequency domain is the impact constant is quite large over a very large range of frequency. So in that large frequency range, it excites the various natural frequencies of that beam, and so it starts showing a spike. That's a broadband excitation, okay? But then if you do the exciter, if you use a specific exciter and come to that particular, very close to that, whatever you found at this point over here at that frequency, 95% of the displacement may be due to that particular mode shape, but random excitation tends to produce an arbitrary shuffling on contributions. Nevertheless, a mode shape is an inherent dynamic property of a structure in free vibration, as if there no other external forces are acting, as if it's freely doing on its own. It represents the relative displacements of all parts of the structure for that particular mode. In this case, X, Z, Y sticking out of the figure. In the fundamental mode of vibration, this will first mode, it will go flapping back and forth like your aircraft wing. If somehow the forcing frequency of that engine is passing through that, it will always pass, whether you know it or not. But you don't want, the pilot should not stop at that frequency. If it does, if the engine, if it does not move out faster or slower, the engine revolution, your aircraft wing at that fundamental frequency will flap back and forth, up and down in the first mode. If that continues on for a long time, it will destroy this attachment and the wing will rip apart. There have been instances of that. In this particular case, is showing if it continues on and the revolution of that engine or jet engine forcing frequency coincides with the second mode of vibration of this angle, this is the modal pattern of that second mode. One side, second side, one side, second side, back and forth with a point of zero displacement. It's an important characteristic. It's called a node point for this mode. Node points are points of zero displacement for that particular mode of vibration. All others are either plus or a minus, because it has to vibrate, right? Plus and a minus. But a node point is a point around which there is no deflection. Keep this in mind. Important point. Node points, by definition, not like in elements, finite element nodes, or this is nodal point. Node point in frequency domain modal analysis is a point of zero deflection. Important ramifications. Important. We'll talk about it later. In design purposes, getting a node for a particular point is an important design parameter to locate a particular piece of machinery or anything which will not get excited with that mode if you are able to do that. Or even if you force it at that point, the second mode will not get excited. Other modes will get excited. A general description, but that particular mode, keep that, we'll talk mode, okay? Nevertheless, a mode shape is free vibration. Sample mode shapes, the mode shape vector. Mode shapes are continuous functions which in modal analysis are sampled with a spatial resolution depending upon the number of degrees of freedom used. In general, they are not measured directly, but determined from a set of frequency response function measurements. You will determine them made between the degree of freedoms. A sampled mode shape is represented by this mode shape vector. You see that? For all these points, it gives a vector, okay, mode shape vector, where R is the mode number for mode 1, mode 2, mode 3. You see? R value, R over here, where is that R? sigma of r, whatever, substitute. So modal displacement. The elements of the mode shape vector are the relative displacement of each degree of freedom, okay, relative to each other. They're usually complex numbers describing it as both magnitude and a phase of displacement. A magnitude and a phase, positive phase or a negative phase. Positive things, both are put together to form the data, okay? You see in this particular mode, it's all some negative quantities. You see that? Phase is shifted from a plus to a minus to give this negative to modal pattern. All right, normal modes and complex modes and all that. I'll continue after 5-minute breaks. All right, Tej?
Yes, sir. Thank you.
Shall we stop here? Okay.
We can stop here, sir. We'll take a 5-minute break at this point, sir.
Shall I exit my screen, right? I'll come back again,
Not
right?
required, sir. We can keep it as such.
Okay, so you can still see my screen. Last time I lost it once before.
Yeah,
and I
yeah,
was
yeah.
continuing.
We can leave it as such, sir. Yeah.
Okay. All right, 5 minutes. Okay.
You can shut your camera if you want. That's all.
Where is my camera?
That start video or this thing.
At the bottom, you can see.
Oh, okay, this one. And this is what happened to me. I did not know what to do, how to.
It's okay, sir. We can just that's fine. You can just leave it
Okay.
as such. Yeah.
You can still see my screen, right? I'm not lost. Okay.
Yeah, yeah. We can see your screen, sir.
Right.
You can keep the lecture slide what that you had right now.
PowerPoint.
Yes, sir. You can
Okay.
leave that on. That would be
What
fine.
is this annotation? Vardhan is requesting to annotate the shared content. What is that?
Sir, good morning. By mistake, I pressed it, sir.
Okay. What do I do?
Some-
Decline?
you can say no. You can.
Decline it?
Yeah,
Okay.
you can decline, sir. Maybe if you accept, I may be accessing your PPT.
Okay.
Okay, sir.
All right. Just give me a few minutes.
Mr. Vardhanam, Professor Bangar Babu mentioned your.
Good morning, sir.
Sir, good morning.
Sir.
Sir,
Can you please repeat again?
yeah, you know Professor Bangar Babu, sir?
Yes, sir. He is my guide. I'm his student.
I see, I see. Okay.
Okay, okay.
Sir, you are with the RCI, sir?
I am in DRDL, sir. I'm working in DRDL, head of structural
DRDL.
facility.
I see, I see.
Yes, sir.
So somebody from RCI, I think couple of.
One Mr. Gopi Krishna and myself, we are from DRDL.
I
RCI
see,
also,
sir.
there might be a few more
Okay.
scientists.
Okay, okay.
Okay.
So what we maybe ask what disclosable work you're doing, sir?
I am head of the structural test facility where we do structural testing of all airframe components, static structural, dynamic structural, and thermostructural. 3 variety of
Oh,
tests
nice.
we do.
Nice.
Yeah, where this model analysis is one part, where dynamics test center will be looking after that.
I see, sir.
So I'll be
So you do
heading
full-scale testing of the frames?
full scale testing of the entire missile. We do this, sir.
I see, sir.
Including static structural where we apply bending moment and do all necessary measurements.
Okay, okay.
then thermostructural temperature along with structural loads. Then dynamics, we do model analysis to find out natural frequencies and mode shapes.
Lot of advanced measurements, I guess.
Yes, yes, yes. We have a 64 channel system. We will be able to cover very big hardware also.
That is nice.
Right, sir. We will discuss later, sir, if anything is required.
Yes, please. Yes, please.
Right,
Definitely, sir.
right, right, sir.
Sir, Tejasvi, what about your WebEx? Now it is fine or?
The live streaming is also going on.
Okay, okay. Live streaming, I think is supposed to stop now in between, not required.
Let us continue as such without stopping anything.
That's better. Huh?
Yeah, there is a question whether these slides will be shared with the participants. Yes, they will be part of the course material.
Yeah, all the slides, lecture slides will be shared.
All right, I'm ready. Sage,
Sir?
can you see my screen? I'm ready.
Yes, sir. We can continue, sir.
Okay, from current slide. Slideshow, current slide. Okay. All right. See, now we are now immersing ourselves into this, various concepts regarding experimental model analysis. So hopefully we have moved away from the mathematical relationship between that domain, this domain, and all that, and focusing more and more into trying to learn more about what the terms are in modal analysis. You guys may be having some questions and all that, but trust me, as you go step by step, and I will be covering almost everything in your minds. I guarantee you that. Okay, by the time, but still we have questions. We leave that to a later stage if I did not cover or re-emphasize it. So let me continue on. The important thing comes up in modal analysis is the term called what's a normal mode and what's a complex mode. Okay, there's a distinction made for these. Normal modes are characterized by the fact that all parts of the structure are moving either in phase or 180 degrees out of phase with each other. The modal displacements are therefore real and are positive or negative. Like for this, in the second mode of vibration, is almost creating a what's called a standing wave with a node point, like I told you, point of zero. This is the second mode for a cantilever beam. Whereas so-called complex modes will show up more because of the way the damping is distributed. Complex modes can have any phase relationship between the different parts of the structure. The modal displacements are complex and can have any phase value. Complex mode shapes can be considered as propagating waves instead of a standing wave pattern, and with no stationary node line. Where to expect, in what type of work that you do, can you expect the so-called normal loads or a complex mode to occur? Complex modes are much more involved in trying to analyze, and much more analysis, spectrum analyzing to separate and all that gets very tough. It's very, it's not that easy to analyze those with complex modes. So the damping distribution in a structure determines whether the modes will be normal or complex. When a structure has very light or no damping, you'll see structures very clearly. Each mode is distinct from it with a distinct node point. Second, third one will have two, fourth one will have three node patterns, all this. So when a structure is very light or no damping, it expects this. If the damping is distributed in the same way as inertia and stiffness, proportional damping, when civil engineers and all that do their work for buildings and all that, you have to, for modeling purposes in finite element, you have to define something, how the damping is distributed. Otherwise, that equation gets very complex. Not that it's not solvable, but there are different techniques. So best way is to say that whatever damping is distributed proportional to the mass and this stiffness, simple ways are there to separate. We'll find normal modes if you use that concept. Structures with very localized damping, such as an automotive body with spot welds and shock absorbers and all those which are all absorbing, distributed in such a way localized, they will start exhibiting complex modes. So it's rather difficult, okay? In these structures, you cannot do by a single input, single output. In order to separate those, you have to get multi-input, multi-output. The whole car will have shakers at various parts, are located, and accelerometers all over, and laser vibrometer fixer, so that those separation of those highly damped modes is possible that way. For highly damped structures, this will occur, and you need much more so that the shaking thing focuses itself, gives enough energy at a particular mode, and gets a response out. Warning: the mode shapes derived from poor measurements can indicate complex modes of structure where normal modes exist. Measurement issues and all that, you got to be careful sometimes. So again, overly dampened structures and all that will create complex modes. Uh, Otherwise, you normally will deal with. This is too much advanced subject to deal with multi-degree, multi-output modal analysis. I can't cover this in this class. But once you guys get good at this, you guys can pick up those somewhere else down the line, and more analysis is needed for that. So in the single degree of freedoms, again, how is the residue related to mode shape? You kept on saying residues, they have a meaning, they have a purpose. Well, the relationship is, we saw that the residue is proportional to the magnitude of the frequency response function at a particular modal frequency, the magnitude is given by, at omega is equal to omega dr, this residue divided by sigma r. It can be shown that the residue of a particular mode r is proportional to the product of the modal displacement at the degree and modal displacement at the input and at the output j at the excitation degree. So the product of these two will give you that residue. The illustration shows the second mode of a cantilever beam. You see that second mode of a cantilever beam with that node point? Built up with all these residues. These are all the residues. And response is measured at 3 degrees of freedom. So the second mode, at 3 degrees of freedom, you made measurements at these three and built up this thing part. We'll see how you take each peak, waterfall patterns they're called, and create this modal pattern. We'll do that pretty soon. And again, an important concept is scaling the mode shapes. Unity, unit mass, remember that? So mode shape vector defines the relative displacements, and the values of the vector elements are not unique. Okay, from FRM measurements, we determine the residues which do have unique values. The relationship between the residue and the associated modal displacement allows us to define a scaling constant for each mode. Okay, a scaling constant, okay, where the scaled modal displacement or driving point is, both are the same, the driving point measure. What we consider as the modal mass is not related to the mass of the structure, and it cannot be measured. It is simply a mathematical device which can have any value except 0. We can choose its value and then calculate the AR associated with that. For simplicity, we'll work with unit modal mass scaling. Okay, scaled modal shapes. From a driving point measurement, we can obtain this for each mode. By using the calculated force from the driving point measurement, we can obtain the scaled driving point displacements for every other point, using that as a unit value. Okay, from the response measurements, we are able to scale. Again, keep in mind, one of the limitations of modal analysis, or whatever, I would not call it a limitation, because really modal analysis gives you what is called a overall modal pattern relative to each mode, which is important in design. Very, very important to know what the relative movements are as opposed to the actual quantifiable data. By the way, don't feel that's not obtainable. Once you get the relative points and you get the accelerometer calibration and the response force transducer, you can always work back those to realistic terms. But they are not of that much importance in modal analysis. That's the key to understand that in modal analysis, the movements, relative movements in each structure are more important to get an idea of the modal pattern so that you can take corrective measures. Like my work involved a lot in helicopter rotor blades, adding viscoelastic damping treatments, and where exactly to apply, where it will have meaning, can only be obtained if I knew the modal pattern of deflection at a particular mode frequency rather than the actual quantity itself. So, like from that perspective. Again, we talked about modal coupling, lightly clamped, light body structure, entire car. You see this? Distinct, clean peaks. It's easy for you to analyze this. But a car like this will show one output, one input, something like that. How do you do it? There's a peak here, there's something else here, there's a one more peak here. This is tough. Heavily coupled modes, complex structures. On a structure that has very heavy damping or high modal density as called, the FRFs do not display clear distinctive modes. The modes are said to be heavily coupled, and the response at each frequency is a combination at many modes. Complex structures can still be described using a discrete set of modes, but the techniques required are more complicated. So these sort of data, multi-input, multi-output devices are there where you can force, and shaker is absolutely essential in these sorts of work. You can't get away with the impact hammers that we do here, okay? What does the modal description assume? There are always some assumptions we need to make, and one is called the concept of linearity. We have to assume that the systems we test behave linearly so that the response is always proportional to the excitation. This assumption has three implications for FRF measurements, frequency response function. Superposition. The measured FRF is not dependent on the type of excitation waveform used. A swept sinusoid will give the same result as a broadband impact hammer excitation because of superposition. Homogeneity. A measured FRF is independent of the excitation level. Reciprocity. Maxwell theorem says that in a linear mechanical system, a particular symmetry exists, which is described by the Maxwell's reciprocity theorem. Civil engineers do that reciprocity. This implies that the FRF measured between any two degree freedoms is independent of which of them is used for excitation or response. See, homogeneous reciprocity. Either impact here and measure the response there, or impact here and measure the response here. We should get the same frequency. That's all superposition, homogeneity, linearity. That's this concept of reciprocity. Okay, that's important. That's an important assumption that we are making in an analysis. In general, structures practically will behave linearly for small deflections, and usually vibrations in its form is not large, okay, small enough, but they will lead to large deflections at the resonant condition. Otherwise, the movements are not that high, but linearity is often violated when deflections become large. So, modal description cannot be used to predict catastrophic failure. We must also assume that structures are so-called causal. They will not start to vibrate before they are excited. Stable, the vibrations will die out when the excitation is removed. And time invariant, the dynamic characteristics will not change during the measurements. This gives some example of time variant systems. As this is removed, mass is coming down, the frequencies and all that will change. Okay, characteristics of some structure will change during a test. Maybe change. The characteristic of lightweight structure may be changed due to transducer loading, where you put the transducer, or long test period structural characteristics may be altered by temperature or other environmental changes. Some structures may be changing continuously. The mass of a flying aircraft, for example, will decrease as the fuel is burned. So the dynamic characteristics of that aircraft are continuously changing from takeoff to landing. That's a tough call. How tough it is. You got to see that on all those components will create different natural frequencies with the mass distribution, reduced mass for a given stiffness. So the engine RPM will try to go pass through from starting zero to reaching very high speeds and then coming down when landing lower speeds. And somehow or the other, because of this characteristics, two things are happening simultaneously. The dynamic characteristics of the aircraft are continuously changing between takeoff to landing because of the fuel mass escaping from that. And if some of the passengers have a tendency to fly off with a parachute and all that, their mass may also be taken into account. The whole idea is the dynamic characteristics and the natural frequencies of aircraft are continuously changing because of these varying parameters. And the forcing frequency while sweeping from zero to high frequencies will somehow or the other meet some of these changing natural frequencies. And so it's a nightmare trying to design those, taking care into all that so that resonances will not occur and the structure fails. Okay. And again, lumped parameter model and modal theory. We talked again. I don't want to do too much on this. One thing to know is that we are moving some so-called uh, the real phase from physical coordinates. Okay, in the matrix equation with the product of the modal matrix, all the scaled and the modal coordinates, we make a transformation into what's called a modal domain. From the physical domain, you move into a modal space where unit modal from a different modal masses and all that, you generate mathematically a so-called unit modal and how at each frequency that I talked about. Each model has a mass of unit modal mass, a damping constant equal to bandwidth, and a spin constant equal to the square of the undamped natural frequency in that domain. Again, this can be mathematically generated. We don't need to go too much into depth and all that. But let's start looking at some practical aspects of degrees of freedom. How many tests, how many degrees of freedom do you need for a test if you're doing a modal analysis? A free point generally has, as you know, 6 degrees of freedom in the X, Y, Z, and rotational degrees of freedom, theta, phi, and psi. I would call it 3 translation, 3 rotation. No suitable rotational transducers are available. So forget these 3. Okay, there's no transducer pickup device. But yeah, translation degrees of freedom are usually sufficient to describe the motion. For most practical structures, a set of regularly distributed measurement points in 1 or 2 directions is adequate. How many degrees are needed for a test, impact test or a modal test? Depends on the purpose of the test, on the structural geometry, uh, and on the number of modes in the frequency range of interest. A test made simply to verify analytically predicted modal frequencies requires only a few degrees of freedom. If the purpose of the test is to construct a mathematical model, then sufficient degrees of freedom must be used for the measured mode shapes to be mutually orthogonal or so-called linearly independent, and not that it's the same one showing with a factor higher and the same mode made pattern and all that. But orthogonal concepts have to be satisfied to prove that they are linearly independent and unique mode shapes. The illustration shows 2 examples of the test measurements made on a rectangular plate, one using 4 and the other using 30 degrees of freedom. So you can have an accelerometer and you can impact, okay, different degrees of freedom, different impacts, but each one has to be defined. 1Z, 2Z, 3Z, defined degrees of freedom, then 3X, definition of response at input at Z, 4X, 4Z, depending upon each direction you impact. You can get any number. For this, you need a multi-channel, multi-channel, more than two to input the various responses, single response, but various impact hammer. No, you define these directions. You don't need using this setup, but you have to define those clearly in your shapes so that you get both this deflection and this movement if you want to get for these. So all that is in a definition how you do it, okay? And each is one related frequency response function for each direction in that response. So all these you'll define more and more degrees of freedom you put, more and more of the modal patterns you can capture and all that, and these definitions. Mobility matrix. The individual frequency response measurements can be arranged the elements of a matrix as called mobility matrix. Okay, each row of the matrix contains of the frequency response function with a common response degree of freedom, while in each column they have a common excitation degree of freedom. So column and row will define depending upon which you are using. So, and then the diagonal of the H matrix, whatever contents of a class are the same. These are the driving point FRFs, H11, H22, H33, H44. All that are the off diagonal or the transfer, and the on diagonal is driving point. If you create a matrix of it, we'll see that with some examples pretty soon. Right now, as soon as this part is over. And mobility, again, don't mistake the word of mobility just like transfer function and FRF. The mobility function is loosely used the word, but in general, the mobility can be described by so-called compliance. Compliance is displacement per unit force, mobility, velocity per unit force, or accelerance, acceleration per unit force. Any of these functions, if you are using a displacement tensor, it's called a compliance function. If you are using a vibrator, the real word is mobility, velocity measurement. If you are using an accelerometer, sometimes it's called inertance also, then it's called accelerance function. But the term mobility is loosely used, acceptable, but really they are generally references. In models, generally references to compliance, displacement. But measurements are usually made in accelerance, using the acceleration accelerometer. Minimum sufficient data and all this. Input output combinations. This is one combination. H1 at 1 itself. Okay. H1Z response at this in the Z direction to impact at 2.2. H1 if you are here. Okay. So each one of these terms, where you are hitting and what you are hitting, is defined by the response and input. Response to input. Response wherever. You see that? And that's how the building of the matrix will be formed when we see pretty soon. Suppose you had wanted to do on a simple structure before we close this, and then we go into modal frequencies are determined simply, modal test on a simple structure. To examine the techniques used to extract the modal parameters, let us look at a modal test on a simple structure, an example of a troubleshooting problem. The example given in the illustration can be considered as a cantilever beam, something like this. You can approximate it as a cantilever of this type, and the accelerometer you put over there, approximation. Okay. The simplest instrumentation can be used is a dual channel signal analyzer with an impact hammer excitation and an accelerometer to measure the response of the signal. We'll restrict the investigation to the first few bending modes of this bending, okay, cantilever beam in bend, degrees of failure. Let us assume that the instrumentation has been set up, preliminary adjustments made, and a few initial measurements were taken to optimize the frequency range. How many modes you want to measure? You decide the spectrum analyzer to capture that, maybe 500 hertz, 5000 hertz, 20,000. Spectrum analyzers can capture up to 25 kilohertz, okay? 25,000. And they're all of not much interest in other works, but mostly it's these up to 500 hertz or things like that. An FRF, any frequency response function will indicate that the beam has lightly coupled modes. Okay, they're lightly coupled, this particular beam. They're not closer together. Therefore, structures behave as a single degree of freedom system around its modal frequencies, around which that they assume that due to that particular mode. From any measured FRS, we can determine the modal frequencies and damping the half power bandwidth into 2 times sigma damping, and thus obtain the pole location. That's the pole location. Pole location consists of frequency and the damping. Remember that? Sigma plus 2 times omega. The modal frequencies are determined simply by observing the maximum magnitudes on the FRF. Whatever the maximum magnitude is, that is the frequency. You read off for this chart. You move the cursor, you pick the cursor here, it will exactly show you on your analyzer what the frequency is. That is the modal frequency. The modal dampings are not so simple to determine and will often be the parameters measured with a greater degree of uncertainty that we know about. One technique we can use to measure the damping is to find the minus 3 dB bandwidth. That's called the half power bandwidth. In logarithmic terms, minus 3 dB is called half power band. On a lightly damped structure, the resonances are sharp and the peaks are too narrow, okay, for accurate measurements of the bandwidth. This problem can often be overcome by making a zoom analysis. You focus onto each mode, zoom it, give it a larger bandwidth within a larger zoom here. If this on 125 hertz, you zoom at in this frequency at 25 hertz maybe or 15 hertz bandwidth, so that you can zoom onto this peak, and it allows you to focus carefully with more resolution points to get the half power bandwidth point, which is nothing but frequency omega 2 minus omega 1 over the resonant frequency omega 3. That's the half power damping. Okay. Alternatively, we can use a frequency weighting techniques in which each mode is isolated in turn. Application of both the some Hilbert transforms and things like that are available, which allows you to refine these things and get the data by using that analysis, finer tuning techniques and all that. The other is mode shape, and most mode shapes are done by what's called quadrature picking technique. Coincident and co-quad, it's called. Within that is the quadrature picking. Remember that the equation of the single
Sir,
degree of
SRM
freedom
University
model.
only in Andhra Pradesh.
Hello? Some question?
Last year, sir, 1 year completed, sir.
Hello, please mute your mic. All the participants are requested to mute.
So remember that the
Neeraj?
equation of single degree of freedom evaluated one was R by sigma, but since our measurements are in accelerants, we need to make a double differentiation of that to get that minus sigma to acceleration model. With more than one defined degree, we can substitute the residues in this form, and giving this form, notice that A is an imaginary number at a modal frequency. This gives to the quadrature picking, real and imaginary. The quadrature is the imaginary component of the magnitude, which is used for picking for mode shapes, through which we can determine the mode shapes. The FRF appears to become purely imaginary at the modal frequency. Its amplitude is proportional to the modal displacement, and its sign is positive if displacement is in the phase with the excitation, and negative if it is out of phase. The mode shapes can be determined if we fix a response or an excitation degree of freedom as a reference, and then make a set of measurements. The imaginary parts of FRF can be picked at the modal frequencies at which they represent the modal displacement. In our example, degree of freedom 2 is used in the response. So let's look at this. How you're doing the hammer test. Okay, fixing your accelerometer at point 2. You're going to impact at point 1, and you look at it'll be magnitude. First of all, magnitude plot, but you look at the imaginary component, the quadrature part of it. Then at this point, there's not much deflection, so you'll see nothing flat. Then you go to this point over here. Okay, what is this? Driving point, impact. Then you look at the imaginary part, you see all of them are facing in the same direction, peaks. Okay, and this is the waterfall plot, by the way. Then you come to point 3, impact. Then you see that each one of the resonance, the imaginary parts, this is positive, This is positive, this will show negative, and this will show negative. Then when you move to your impact hammer to 4 and capture the imaginary components, this will show a positive, this will show negative, this will show all at the same frequency. These things will not shift. The frequency will be the same every time. It's just that the imaginary components will either go up or go down at that particular frequency. Now, take the same thing and make a waterfall plot of it. Okay, the frequency view for the first one at this imaginary component. Okay, if you plot all the things for the first mode frequency, one wherever that is, one positive, positive, positive. You see that? You fit all those, you get the first modal pattern for the first frequency. Then the second frequency, at the second frequency, the modal pattern is described by the first 0, then the second one here, then the third one there, and then the fourth one is negative. You see that? Negative. So this is the second modal pattern. And same for the third one. Okay. And for the third frequency, for the third natural frequency, you start fitting. First was a 0. Third one. Second one was this peak. Third one is negative side. You see that negative side? And then third one, fourth one is again went up there. So on. If you go on fitting more and more. So this is called the quadrature picking. The quadrature picking method of creating the modal pattern, mode shape. That's all the spectrum analyzers and your softwares are doing. They're gathering all your data from the log magnitude. The real components and imaginary components are separated. And if you are using the displacement and the acceleration functions, the imaginary components will give a difference of at each. Again, the key to understanding fundamentally is that each one of these frequencies, the 4 which are defined initially, they will not shift wherever you may hit on the structure. They will be the same. Sometimes they may go to 0. They won't show. And that zeroing is called a node point. Okay, when it goes for moving, and there's zero deflection at a particular, there's a node pattern moving. So in a frequency view, viewing from this end frequency as a function of omega, you're viewing these ups, downs, up, downs as a waterfall. Here, the next waterfall behind it, behind it, behind it. So it's a 3-dimensional picture, and you're curve fitting the third dimensions of this, and this, and somewhere else if you have to get the first mode pattern. And at the second frequency, you're going to curve fit this with this fellow here and this fellow here to get the second modal pattern. And at the third frequency or fourth frequency, if you had created, I would have got a pattern here up, a pattern down, and then a pattern down over there. So that's all as you go along. If this is for a cantilever beam, if you had a plate coming out of this, same curve fit routines are done in the third direction also, and you get a whole blown out total modal pattern that you see. Again, frequency response function is simply a linear system in a black box, like a black box. Okay, it'll have inside it the ratio of the output to the input. That's the frequency response function definition. Measuring specific function, resonances in operational may be considered as structural weaknesses. That's what you remember. Why are you trying to find out a resonant condition in a structure? That gives an important criteria for the structure that that part at that frequency is weak. It's weak. If you somehow force the function to excite it at that point and it's sustained for that position, the severity of a resonance depends on the magnitude of the frequency response function between where the operational forces act on the structure and where the response is observed. And if we continuously keep it at that point because of its structural dynamic weakness as opposed to static weakness, okay, dynamic weakness will cause failure and all that. Excitation. You need to have some excitation, dynamic force for this structure. How do you do that? What are the various forms? Excitation waveform will limit ourselves to waveform which have energy distributed over a wide band of frequencies. This can be simultaneously excited. It's important to simultaneously excite as many frequencies within the structure. One of the best ones is the hammer. Hammer has a transient, sharp transient is equivalent to a sudden boom like this, and that transient history in the frequency domain will have a large content. At some point, it will die away. Okay. Shakers will have some sort of a random excitation is equivalent to get enough energy. Okay. Eccentric mass, swept sign testing and all that is a sweeping technique. Certain parameters should be considered before setting excitation, application, spectrum control. Crest factor is important. Linear or non-linear structure, speed of the test, what is the equipment available, all of them play a role on what you decide. Hammer, this, random excitation. If the purpose of the test is only to measure natural frequencies, then the precision required is much less than when the measurements are to form the basis for a mathematical model. The cost of extra precision lies in the time taken for the measurements and the cost of instrumentation. Spectrum control is the capacity to limit the excitation to the frequency range of interest. Okay, you got to see the interest. You don't want something way beyond. How many peaks do you want to get? Accordingly, you got to get control the spectrum. If you are enough for the first fundamental, enough energy to count at. If you lot more and all that, some more and all. A very important factor is a crest factor, which describes the peakiness of the signal. It is defined as the ratio between the peak and the standard deviation RMS in the signal. A high crest factor in the excitation form will have two disadvantages. The signal to noise ratio is decreased since the instrumentation must make allowances for the peaks and some of the signal is lost in the existing noise. High peak forces can provoke non-linear behavior in the structure. We do not want that. An expectation of non-linear behavior in structure raises the question, do you want to describe the non-linear behavior or do you want to make a linear approximation? Modal analysis assumes linear systems and linear models. If we deal with a structure exhibiting some non-linear behavior, we generally attempt to make the best linear approximation. Is selecting a waveform that excites the structure over a wide variety of levels randomizes the nonlinear behavior, which is then averaged out. You go on averaging. You don't just do one hit and get away. To stabilize it, you take 5 averages. At least a minimum of 5 we do for our work with the impact hammer. To study nonlinearities, sinusoidal excitation with maximum amplitude is generally used. There are too many nonlinearities. And how do you implement excitation? What sort of excitations are there? Excitation forces can be generated by many different kinds of devices. For broadband excitation, we'll consider two classes. Examples of attached exciters are electromagnetic shaker, electrohydraulic shaker, eccentric rotating balance types of these shakers. More exotics as rockets or guns and all that. Excitation, some sort of exciter. You want to move the structure, okay? Examples of non-linear, non-attached exercises. These all have to be physically attached, okay? Electromagnetic and this and that. Non-attachable hammers, large pendulum impactors, suspended cables to produce a snapback. Acoustic excitation cannot be used in modal analysis since control of direction and excitation is not possible. Acoustics is a all-around thing. It can be used, however, for checking modal frequencies producing unsealed mode shape. Force measurement. How do you measure the force which is being given by a transducer, by a shaker? It's called, there are force measuring devices which will measure the force. It's introduced between the structure and the exciter through what's called a stinger. It's important. It's not directly connected. It's a nylon or steel which is flexible, quite flexible, thin column. Okay, it's important. If you put it very rigid, then when the beam is vibrating, when it's reversing in this direction, this rigidity will cause a false listing and give you a higher frequency. So it should be have the stingers are important. This is important design. It's very tough to get this accuracy. Okay, but sometimes when exciter is needed, you have to put a forcing function. So in between a force transducer, it's a simple device which has in it a crystal which when compressed will give output signal proportional to the force. So the exciter attachment is very key when you use this sort of exciter. And response transducers are any motion parameters, displacement, velocity, or acceleration can be measured. The best choice is the piezoelectric accelerometer for the following reasons. It gives good linearity, very low weight, very small size accelerometers are coming into the market now. From the time we use larger one was seismic and all that. Broad dynamic range, wide frequency range, 0.2 to 10 kilohertz. Strong construction, simple design. Some tips can withstand shock of 20,000 grams, but be very careful. Don't ever, when doing a test, be very careful. Tie that accelerometer wire carefully so that it doesn't fall on the floor. I have enough of those destroyed in the lab and it just drops on the floor. It creates a high shock level, high environmental resistance, low transverse sensitivity. There's no transverse vibrations are not picked up. It's all in that. Unless you have a triaxial accelerometer, X, Y, and Z, then all will be picked up. They are also there. Velocity or displacement parameters can be readily obtained through integration. If you want acceleration, you can get others, either through a conditioning amplifier or post-processing analyzers. Transducer mounting, how do you do? Very many ways are there. Very common is a steel stud. Most common is beeswax. It's just enough to glue it together and enough testing. Okay, some ships like the variations, cement stud, thin tape, thick tape, magnet, different types are there based on your application. Loading, that's important. Mass loading. The weight of the accelerometer should not be greater or anywhere closer to the weight of the structure. You have to choose that very carefully. A rule of thumb is to use light transducers and light structures to give minimum loading. Otherwise, the mass of that is also added to the mass of the structure and give a frequency which is not real and true, right? So, since even a low byte accelerometers can significantly check a local resonance, okay? Consideration should also be given to the addition of stiffness and damping due to bending or friction at the mounting interface, wherever you're mounting. Frictional losses in a clamp will add on damping. Once again, small transducers should be used for high frequency work together with the mounting technique. Random excitations generate completely random. Okay, again, it's all random. Signals can be generated. An electric propellers will give you a signal which is equivalent to a kind of random excitation. Sometimes it's called a pseudo random, which will give a sort of a repetition, chup signals, which are random in nature, and they're pretty good at capturing a lot of this data, but they are in a periodic nature. Okay, chupping this thing, and most common that you folks will be doing in general will be the impact excitation. Most common, the most popular excitation used for modal analysis is impact hammer. The waveform produced by an impact hammer is a so-called transient, a sudden, okay, sharp. The spectrum is continuous. For this time domain, the spectrum for that will be continuous. At some point, it will fall off. So there will be a useful range over which you have to use frequencies. If you are capturing 4, 3, or 4, they better all be within this drop over there. So you can increase or decrease the spectrum by adding mass and type of tips. We'll talk about that. It's a periodic structure with the duration, and that the shape of the spectrum is determined by the mass and stiffness of both the impactor and the structure. For a relatively small hammer used on a hard structure, the stiffness of the hammer tip determines the spectrum. We'll talk more about that later, different tips. The hammer tip acts as a mechanical filter. Impact hammers are constructed by adding a force transducer between the hammer. This is a force transducer, just like a shaker, okay? Adding a force transducer to the hammer and adding a stiffness coupling member, okay, so that this stiffness is maintained. Caution, the measured force is the mass of the impactor behind the piezoelectric disc of the force transducer, okay, multiplied by the acceleration that is being, how you are hitting it and all that acceleration level. The true force exciting the structure is equal to the total mass of the impactor, including the force transducer and the tip, multiplied by the acceleration during the impact. The true force is the measured force multiplied by the ratio of those two quantities. Hammers can be constructed with weights ranging from a few grams up to several tons. They use larger size hammers on, massive structures, okay, covering the frequency range 0 to 5,000 with the smallest hammer to 0 to 10,000 with the largest hammer. So, and then advantages hammer testing are speed. Just need few averages, 3-4 averages to get a good enough signal refined. No elaborate fixtures. There's no variable mass loading of the structure. This is particular advantage with light structures. Is changing the mass loading from point to point can cause shifts in modal frequencies. It is portable, very suitable for measurements, relatively inexpensive. And I said the type of tip can vary the content of the signal. If you use a steel tip, you see it's very sharp. You have a large content of frequency range over which. If you used a plastic tip, well, it changes, it drops off nearer. If you used a rubber tip, it's even lower like that. So it all depends on how many modes in the frequency content you're analyzing, where they would be, and accordingly you choose the tip. So there's a lot of fine tuning and all that refining you do before you actually do your modal test and comfortable by doing some trials and errors and getting the data. But then using the hammer, what are the disadvantages? The high crest factor, so-called sudden spikiness sharp, makes the technique unsuitable for testing systems with nonlinear properties, since the nonlinear behavior will be provoked to apply sufficient energy to a large structure. Very high peak forces might be required, and the structure may become damaged locally. You can't go and bang on a structure which is, of this type, and you'll form a dent and destroy. That's not the idea. Okay, so those some you got to be careful. The signal is highly deterministic, and the force level only varies slightly between overload and trigger, underload levels. There's a good way to set your trigger level in your spectrum analyzer so that you don't overload. If you overload it, you're getting a garbage signal out, coherence functions and all that, which we'll talk about. How much of the output is because of the input and how much is because of noise is what defines a coherence function. We'll talk about it later in some of those. And due to the deterministic nature of the signal, the coherence function cannot show either leakage or nonlinear behavior. The spectrum can only be controlled at the upper frequency limit, which means the technique is not suitable for zoom analysis. Okay, so at this point, I have given you all a general picture of what is all involved, the impact hammer, the exciter types and all that. And now my goal is for my next last lecture for today, make use of one lecture 6. I'm coming to lecture 6. I'm going to talk about okay. Can you see my screen, Tej?
Yes, sir. The sound and vibration magazine is visible.
Okay. All right. Now we are going to tie up all the thing we talked about into doing actual modal analysis, experimental modal analysis. And I have found over the years teaching the subject, the article by Peter Avitable on this concept of modal analysis to be extremely well done and extremely useful. So I plan to share my lecture 6 by tying up based on his article and his work in a simple non-mathematical presentation. Extremely well done job. And over the years when I offer this class to my students, I make this an essential reading assignment for them to go through and come back to class, come prepared, and we go through this step by step. So my request to all you folks in, who are attending this if you're not able to read any of the other material and you're crushed for time and things like that, at least read this part of the article thoroughly from end to end, which I'm going to go through anyway, point out the important features, and and which will give you a very well done, very good concept. He's a excellent teacher and excellent presenter, and gave quite a lot of articles trying to come out with the so-called simplified form of making a complex subject easy to assimilate and understand by various people. I like the technique and all that. So not only this particular article, which is important, apart from that, each and every item that we talked about here, he goes through much more detailed analysis, and several articles is put together in the Society for Experimental Mechanics, experimental techniques part, a lot of them, and some of them I'll be using in my class to elaborate on some items, but I have all of them with me available, and anybody wants to go detail in particular one, we can make them available. I can provide them to Tej, or he may have access to them too, those sub articles in SEM. So my next goal, and what is the time, Tej? How are we doing for time?
Sir, we have another 4 minutes before we take a break.
Okay, and once we come back from the break, I will go through all of you this setup here, and once again, like I said, if you have nothing better to do during a daytime and things like that, I would strongly suggest to read up this article. This will answer as many of your questions as possible, even for your quiz or whatever test you have and all that. It is all defined in some of these concepts here, and my goal is to use this before moving on to other materials from other sources for the rest of the lectures. Okay, so we will come back from the break. We'll go through as much as we can within the time today. 1 more hour, I think I can complete. If not, I'll continue on tomorrow. But this is the most important article of my entire series of lectures and all that. I found this to be useful once again, and acknowledge the wonderful work done by Dr. Avitagul over the years at University of Massachusetts Lowell. Fantastic, and they give seminars and this all over the world and all that and everything. Okay, so we'll come back and then continue on with this non-mathematical presentation of this course.
Thank you, sir. Now we'll take a short break. Thank you.
Okay, thanks.
I request all the participants, I think it is very much interesting. The next lecture is some of the mathematics which were discussed in the last couple of lectures. Same thing is explained in easy way by Peter Evitable without much of mathematics. So the entire concept has been explained. I think with that you will get complete picture of what is experimental model analysis. Okay.
Sir, is a PDF of this article available? The magazine article.
Yes, I have provided you that copy. In my folder, it is there.
Right, sir.
Yes, it is there. I made that available. It's the same, but it's much more cleaner. The version I gave you, this is from the magazine itself that I have with me. But Suman was able to get that copy from a source, and he made that attachment in my folder for me. Shall I start?
One more minute, sir, and then we'll start.
Okay. All right.
Is it as a separate PDF file, sir? Day 2 lecture 6. Right.
It is there under lecture.
Day 2 lecture 6. Right, sir.
Lecture 6. Yes.
Got it.
Got it. That's a PDF, right?
Yeah, that's the PDF, right?
And it's a better quality than the one I have. This is from my class notes and highlighted one.
Right, sir. It's 10 a.m. and
Okay.
yes, sir. We can start.
And I will do this. Hopefully, I may cover. If not, after 1 hour, I'll continue the rest tomorrow. Okay.
That's fine, sir.
Okay. All right, folks. Again, my sincere advice and my request to all of you is to spend some time reading this article. I'll cover the key points as much as I can, but again, all your questions and as much NMA questions as possible would be answered. I do the same thing to my students. They keep asking this, that. I said, hey, first take this reading assignment, take a whatever time you like, come back. Then I start my lectures. Then they already have the answers for me before I ask. So I encourage all of you, because you are from different concepts, different backgrounds, and different industries or whatever. This has been written for that sort of a exercise to tie it up. So that's my encouragement. Okay. The intent again of this article is to simply identify how structures vibrate from a non-mathematical perspective. With these being said, let's start with the first question that is usually asked. Could you explain modal analysis for me? Once again, apart from these 6, 7 pages in this article, each and every question again in repeat, much more detail have been covered by Petra Avoidable SCM. Maybe I did not attach those because I'm not covering all of them page for you. So only few of the articles which I'm covering in this lecture I have, but we can provide you those if you're interested. And I thought you had access to those too for a detailed, you wanted to make a reference manual, right? So we can get you that. So in a nutshell, we could say that modal analysis is a process whereby we describe a structure in terms of its natural characteristics called frequency, damping, mode shapes, like I said, and they're called the dynamic properties. Okay. Let's consider the freely supported plate like shown in figure 1. Maybe I get these two side by side. I don't know, this is a PDF. I may not be able to do that. So let's see a simple plate excitation response, input and output response. Okay. We will change the rate of oscillation of the frequency, but the feed force will always be the same value. You can maintain an exciter but a particular force, but go on changing the frequency. Amplitude is the same, but frequency can be changed. Only the rate of oscillation will change. We'll also measure the response of the plate due to excitation with an accelerometer attached to the plate of the column. Now, if you see the measured response of the plate, we'll measure the amplitude changes as we change the rate of oscillation. So as you sweep the oscillation changes in the time domain, you will see suddenly some this thing, and then after this, and this is the increasing rate of oscillation, simple plate response. Okay, so that's what is happening as you move along. What are they? There will be increases as well as decreases in amplitude at different points as we sweep up in time. This seems very odd since we are applying a constant force to the system, yet the amplitude varies depending on the rate of oscillation of the input force. But this is exactly what happens. The response amplifies as we apply a force with a rate of oscillation that gets closer and closer to the natural frequency or the resonant frequency of the system and reaches a maximum when the rate of oscillation is at the resonant frequency of the system. When you think about it, that's pretty amazing since I'm applying the same peak force all the time, only the rate of oscillation is changing. Meaning what? Even a small peak force at a resonance frequency can create large of oscillation because of the concept of resonance. Remember that. You don't have to have magnitude enough. Even a smaller force, but applied at a frequency. So this time data provides very useful information, but we take the time data and transform it to the frequency domain using FFT, then we can compute something called the frequency response function as shown below. Now there are some very interesting items to note. We see that there are peaks in this function which occur at the resonant frequency of the system. And we notice that these peaks occur at frequencies where the time response was observed to have maximum response corresponding to the rate of oscillation. So you see that here, as you hit here, you see this peak showing up in the frequency. Each one of this is related to that thing going on. You see that? Showing up that response suddenly the input force, constant force input force, but the response is shooting up because it hit the natural frequency of that plate. Inherent property of the plate, the dynamic property of the plate coincided with that outside. Now if you overlay the time trace with the frequency trace, what we'll notice is that the frequency of oscillation at the time with which the time trace reaches its maximum value corresponds to the frequency where the peaks in the frequency or response reach a maximum. So you can see that we can use either the time trace to determine the frequency at which maximum amplitude increases, or look at the frequency response function. A much better way to determine where this natural frequency is. Clearly, the frequency response is easier to evaluate. It's not easy to determine using time signals to get what is going on. No. This is a better concept. I would prefer this any day compared to that, okay? And let that analyzer do all the dirty work for you and display those. Most people are amazed how the structure has these natural characteristics. Well, what's more amazing is that the deformation patterns at these natural frequencies also take on a variety of different shapes depending upon which frequency is used for the excitation force. Meaning that at this frequency, the deformation of this plate will be different from the deformation pattern in mode 2, if you call that mode 2, mode 3, mode 4. The deformation patterns for each will be different. Okay. Now let's see what happens to the deformation pattern on the structure at each one of these natural frequencies. Let's place 45 evenly distributed accelerometers plate and measure the amplitudes of the response with different excitation frequencies. And what it did was, I don't know whether it showed that over here, figure 6, figure here. He got those, and he shows you that after doing, picking up the data, in the first mode of vibration, that plate, it's a free plate, it looks like, will cause a bending mode like this. And at the second mode, by picking up both those accelerometers and all that he talks about, at the second mode of vibration, the deformation pattern, if you capture, will be a twisting mode. It's the first mode of bending, first twisting mode, then second mode of vibration, the third mode, second bending mode, pure bending, and fourth mode is a complex mode, a bending and a twisting mode. You see the pattern as you go along, so on and so forth. You can by modal analysis By doing the imaginary parts of those various impact, response, impact, pick up at this, all over 45, whatever he said, you can create this. At mode 2, at this point, all the imaginary components of this waterfall of all this, if you create and join them together and let the software replot it for you, it will go on twisting mode back and forth like this. At this frequency, all the data, 45 transducers and all that you pick up and all that, and redisplay the imaginary components and animate it. The beauty with the software is you can put it in a loop, it will animate, it will go on showing back and forth, and so on and so forth. That's what he's trying to tell you over here, that these natural frequencies and mode shifts occur in all structures that we design. Basically, there are characteristics that depend on the weight and stiffness of my structure, which determines where these natural frequencies and mode shapes will exist. As a design engineer, you need to identify these frequencies and know how they might affect the response of the structure when a force excites the structure. Understanding the mode shape and how the structure will vibrate when excited helps the design engineer to design better structures. If you know something, you can improve on it or make changes to it. There's a whole field of what's called structural dynamic modifications, which is a whole field in itself, which is based on the concept of modal analysis. You get the data from it and you do fine tuning, you use the absorbance and move the stiffness, move the mass, see what changes it does and all that. That's called structural dynamic modification. There is a much more to it all, but this is just a very simple explanation of modal analysis. Very good job to tell you what is going on. Basically, modal analysis is a study of the natural characteristics of the structure. Understanding both the natural frequency and mode shape helps to design my structural system for noise and vibration applications. We use modal analysis to help design all types of structures, including automotive structures, aircraft structures, spacecraft, computer, tennis rackets, golf clubs. I was involved in trying to optimize the impact and response of golf clubs on the head hitting part and trying to figure out which points where the maximum node lines are passing, because that gives an idea of what's called a sweet spot. If you hit on that sweet spot, even on a tennis racket, if you for those of you who play tennis, there's a sweet spots region which is identified on the tennis racket. If you hit at this sweet spot, if the ball hits there, you won't feel a jerk on your arm. Anywhere else the ball hits, then you'll feel a jerkiness in your arm in this one. So getting a large, sweet spot on tennis rackets is a good sales technique for tennis racket manufacturer, because more people can start playing without feeling bothersome. And dynamically, we were able to characterize on a tennis racket by saying for various modes, most of the node lines, remember node point for a beam was a point of zero displacement. But in a 2D structure like a plate, it's a joining of all the node points of all will be a node line. So wherever maximum node points are concentrated, that will be the sweet spot, because that's the point of zero deflection for that many modes. Meaning that if something is impact there, it has no response for those particular mode. Other frequencies may get excited. So things like that is used. See, look at that. So many applications. Introduce the measurement frequency response functions. It says, what are these measurements that are called frequency response functions? Is a very simple ratio of output response for the applied force, right? H omega. Remember, we measure both the applied force and the response of the structure simultaneously. And response can be any form: displacement, velocity, acceleration, doesn't matter. If you can get one, you can get the other. Now, the measured time data is transformed from the time domain to the frequency domain using FFT analyzer found in any signal processing and computer software packages. Due to this transformation, the functions end up being complex value numbers. The functions contain real and imaginary components or magnitude and phase components, because it's a complex number. It will have a magnitude and a phase. And a magnitude will have as a complex number, real and imaginary. Square root of the real square plus imaginary square will be the absolute value of the magnitude. So let's take a look at what some of the functions might look like and try to determine how modal data can be extracted. Let's first evaluate a simple beam. We did that exercise. From this he extracted how the first mode, the second mode, the third mode. You see, a third mode will have 2 node points, and the fourth mode will have 3 node points. If you go on mode, if you go more and more data, you can get more and more node points. And it simply describes this as notice that the beam has 3 measurement locations in 3 mode shapes. These are 3 possible places that forces can be applied and 3 possible places where the responses can be measured. It is not restricted to that. This is a cube. If you want to finer this thing, take more and more mode points. Then you'll get a finer definition and smoothness and all that. But is it necessary? Is it essential? You can spend more time in doing all that. So this means that there are a total of 9 possible complex valued frequency response functions that could be acquired. The frequency response function is usually described with subscripts. Remember Hij, which denote the input and output locations as H of out to in. Remember, I is the out response and in hammer, or with respect to typical matrix location is, if you put it in the matrix, the row part I, J is the column, correct? So you can create a matrix with those. Figure 7 shows the magnitude, phase, real and imaginary components. Here, figure 7, for those, all the 6 parameters, if you hit, this figure 7 shows you the response measurements as obtained, where you hit and what you hit. This is the driving point measurement, driving point measurement, driving point measurement. And the second one, the row. And you see one of them has disappeared because if you might hit it at a node point. I think in this particular case, the fellow hit that at a node point. You see, number 2 was the node point. The second mode won't show up if you hit at that node point. That's why node points are dangerous. You may miss a mode, and if you see a spectrum, you might immediately start counting first, second mode. But you missed this in this because you hit at a node point. That's why a driving point measurement is very, very important, which will give you all the modes existing in the structure in the driving point measurement. So this is the row, this is the columns, okay? Magnitude, then phase part below that. The spectrum analyzer has at least 4 or 5 screens, which immediately shows you for a given magnitude, the phase, and within that phase, the real parts and the imaginary part components over here. And you see that all the imaginary components are showing either down, up, down, down, up, down, up. And these are the ones you're cut fitting at each, like I explained to you before. Okay. So one question that always seems to arise is whether or not it is necessary to measure all the possible input-output combination, and why is it possible to obtain mode shapes on only one row or one column? Why is only one row or column of the apparent matrix needed? That's a good question, right? It's very important for us to understand how we arrive at mode shapes from the various measurements that are available in the frequency response function matrix without getting mathematical. Important. Let's discuss this. Okay, let's just take a look at the third row of the frequency response function. Concentrate on the first mode. If I look at the peak amplitude of that mode and all that, what's showing you, like I said, it picks up. Now look at the second row. Which one is it referring to? First row, second row, third row. All these things over here, those functions. Okay, the exercise, whatever I did, if you read more, it'll give you all those. So this points out one important aspect of modal analysis and experimental measurements. The reference point cannot be located at the node of a mode. Otherwise, that mode will not be seen in the frequency response function measurements, and the mode cannot be obtained. So it's a little bit tricky. If you don't know, you will pick a node and you will miss the data. So that's why you try to do more of them so that you don't excite at a particular node and lose it. Okay, so that's why more distribution is done and all that there. What's the difference between a shaker test and an impact test? Okay. From a theoretical standpoint, it doesn't matter whether the measured frequency response function comes from a shaker or impact test. Let's see figures 11A and 11B. What's 11A? Great here. This is all describing the 9 and 10 over here. Figure 10, fact, you guys can read this to show how the hammer and all these, how the curve fitting was done to take, which I explained to you. So where is this rover? From a theoretical standpoint and impact test, let me go down. Impact hammer and test of the frequency, whereas the shaker test generally results in measuring one of the columns of the response matrix. Okay, impact test measures the rows and shaker test measures the column. You see this impact test, and a shaker test will measure, one shaker at one point, and you will move the accelerometer to different points. Okay, to get the setup. It's much more difficult to move the shaker like the impact hammer. Okay, usually in a shaker test, you will excite with one point and pick up with different points of the accelerometer and get the column, whereas you'll get the rows with the impact hammer test over there. That's the only difference. And the other advantages, of course, is that it's concentrated energy and all that over there. But the case shown, the third row is exactly the same as the third column. If you measure those two, exactly they'll be the same. Theoretically, there's no difference between a shaker and an impact test. That is from a theoretical standpoint. If I can apply pure forces to a structure without any interaction between the applied force and the structure, and I can measure response with a massless transducer that has no effect on the structure, then this is true. But what if this is not the case? There'll be some issues like that, fixturing and all that, performing it just from a practical standpoint. The point is that shakers and response transducers generally do have an effect on the structure during the modal test. The main item to remember is the structure under test is not just the structure for which you would like to obtain modal data. It is the structure plus everything involved in the acquisition of the structure data. The structure suspension, the mass of the mounted transducers, the potential stiffness account of the shaker stinger arrangement. Remember the thin rod? It has some role, if it's very stiff and all that, dangerous. It should be flexible enough. So while theory tells me there shouldn't be any difference between the impact test results and the shaker test results, often there will be differences due to the practical aspects of collecting data. The most obvious difference will occur from the roving of accelerometers during a shaker test. The weight of the accelerometers may be extremely small relative to the total weight of the whole structure, but their weight may be quite large relative to the effective weight of the different parts of the structure. This is accentuated in multi-channel systems where many accelerometers are moved through around the structure in order to acquire all the measurements. Several impact output response, XYZ, XX, XY, XG, YX, YZ, YX, all combinations, all of them can be thrown in and separated out by methods of, curve fitting and all that to get different directions and all that. Exactly the same. Output, input, ratio of output, input. Okay? So multi-channel systems where accelerometers, this can be a problem, especially on lightweight structures. One way to correct this problem is to mount all of the accelerometers on the structure, even though only a few are measured at a time. And there are ways to add dummy accelerometer masses and all that not being measured. So it's talking about some of the issues involved and how to compensate for those. And the difference that can result is due to the shaker stinger effects. Basically, the modes of the structure may be affected by the mass and stiffness effects of the shaker attachment. While we try to minimize these effects, they may exist. The purpose of the stinger is to uncouple the effects of the shaker from the structure. However, on many structures, the effects of the shaker attachment may be significant. Since an impact test does not suffer from this problem, different results may be obtained. If you repeat the test with a shaker and that, some of the differences you may observe in frequencies and all that are because of that particular shaker stinger, not being not purely flexing when the structure is moving, but creating a force back and increases the stiffness. So while theory may says that there's no difference, there are some very basic practical aspects that may cause some difference. What measurements do you actually make to compute the FR? The most important measure is experimental is the frequency response function. Very simply stated, this is the ratio of output input to input excitation force. It's typically acquired using a dedicated user FFT analyzer, data acquisition system, with a software which collects all the data and reproduces that components. Discuss some of the basic steps. These analog signals must be filtered to assure that no what's called aliasing of higher frequencies into the analysis. Aliasing is the important part because the moment you capture some other extra frequencies may creep in and distort. This is usually done by there are filters which are able to separate out these higher frequencies and analog filters in the printout called anti-aliasing filters. Their function is to remove any high frequency signal that may exist in the signal. And they're there, they're available. That's digitizing the analog signal to form a digital representation of the actual signal. Measured analog converters, analog to digital converters are there, which is 10, 12, 16-bit converters. The more bits available, the better the resolution possible in the signal. Some of the major complaints lie in sampling issues and all that, how many signals to compute and all that. And what's called leakage errors occur from transformation of time to the frequency domain. And now for each one of these, there is a facility available to you to compensate, like windowing functions and all that, which we'll talk more about them, okay? The Fourier transform process requires that the sample data consists of complete representation data for all time or contain a periodic repetition of the measured data. When this is satisfied, then the Fourier transform produces a proper representation of the data in frequency minimize the distortion due to leakage. Weighting functions called windows are used to capture the data. We'll talk about more windows. What type of windows are there? And later on, tomorrow's lecture, I believe we have that. While windows greatly reduce the leakage effect, it cannot be completely removed. Okay, only the data are sampled, then the FFT is computed to form linear spectra. Averaging is performed on the spectra. The main average spectra computed are the input power spectrum, the output power spectrum, and the cross spectrum between the output and input. These functions are averaged and used to compute two important functions, the frequency response and the coherence. What is that coherence? The coherence function is used as a data quality assessment tool which identifies how much of the output signal is related to the measured input signal. The FRF contains information regarding the system frequency and damping, and a collection of FRFs contain information regarding the mode shapes. This is the most important measurements. And I believe we showed you a coherence function here. I don't know. I'll talk about it more. We separate this thing. Coherence is, I think it is here. Coherence. You see the coherence function? If all of the output is because of the input, it's almost one. If some of the outputs coming is because to noise, there'll be a drop in the coherence function. Okay, you don't want at this point see the drop in coherence function. Perhaps this coincided with a particular 50 hertz or 60 hertz electrical signal, depending upon where you are. I believe in India is 60 and 50 here. So if you see a spike somewhere over here, watch out. Check the coherence function. If it is very, very low like this over here, that's not a good signal. For all other, wherever the resonant peaks are there, the coherence function should be almost close to 1. 0 to 1, coherence function is defined. And this gives you how the input signals, analog signals, applying windows, all this other data. You can read through those and more data. Let me see what are the biggest things to think about when impact testing. First, selection of the hammer tip can have a significant effect on the measurement acquired. The input excitation frequency range is controlled mainly by the hardness of the tip selected. The harder the tip, like I told you, the wider the frequency range that is excited by the excitation force. The tip needs to be selected such that all the modes of interest are excited by the impact force or the frequency range of interest. So it's a trial and error. You choose it with a tip, do a driving point measurement, and see how many peaks are showing up. If you're satisfied at 3, 4 peaks, then use that tip. If you want more, go for the harder tip or mass increase, various things you can do. The input power spectrum does not excite all of the frequency range, so they roll off. At some point, it roll off. Typically, we try to have a fairly good and relatively flat input excitation force. The frequency response function is measured much better, as evidenced by the much improved coherence function. It gives you some examples of the different. For impact excitation, the most windows. What is windowing? Okay. The second most important aspect relates to use of an exponential window for the response transducer. There are several windows, flat window, this window, that window. For impact 10, what's called an exponential window is used, so that you are forcing that signals to die off, so that extra data is not taken into account. Generally, for lightly damped structures, the response of the structure due to the impact will not die down to zero by the end of the sample interval. When this is the case, the transformed data will suffer from a digital signal flow passes referred to as leakage errors. In order to minimize the leakage, there are functions available. What type of window you want to use on your this thing on a spectrum analyzer. A highly desired window is a weighting function referred to as a window is applied onto the data. This window is used to force the data to better satisfy the so-called periodicity requirement. So for impact excitation, the most common window is called the response transducer measurement is the exponentially decaying window. Implementation of that is shown in figure 14. Figure 14, where is that? Figure 14. Here, see, exponential window, okay? If left as it is, the side signal will go on like this, okay? And forever and all that, these are leakage errors. So the sample signal will be like here, there's a loss. So you force a window, choose the window, it will see that the repetition of the cycle will force it down. In a way, it will indirectly add a little bit to the damping, but at least the window signal will be clean and neat in order to take the data. So if you're not really too much bothered about the actual damping values and you just want to have a general idea, this exponential is the best window to have a good data output by using that function. Otherwise, they are called flat top and other, but this is strongly recommended, okay? Consider some of the testing consideration of shaker test. What are the biggest things to think about when shaker testing? That's impact testing and shaker. More common excitation still used is random excitation due to the ease of implementation. However, due to the nature of this, leakage is a critical component. At that point, use what's called a Hanning window, which is provided, which allows you to use that to make it average. Auto ranging and averaging with this window will force you to have those sorting, which is repetitive in nature, as called. This leakage effect is serious and causes distortion of the measured frequency response function, even when those are used. A typical random excitation with a Hanning window is shown in figure 15. As seen in the figure, the Hanning window weighting function helps to make the sample signal appear to better satisfy the periodicity requirement of the FFT process. The FFT process will do a lot of things based on some periodicity that is to be generated. And that's why these sort of techniques are used to make that better without any leaking. Two very common excitation signals regularly used are burst random and sine chirp. Sudden burst random or chirping, okay, going on giving signals and shots and all that. Both of these have a special characteristic that they do not require the need for windows to be applied to the data, since the signals are inherently leakage free in almost all testing situations. You're giving a burst sign, chirping, things like that. So they're already compressed and within range and repeatable and all that. So all these other issues, if you want to avoid, choose something like that, which will get enough content to excite. In the case of burst random, the periodicity requirement of the is satisfied due to the fact the entire transient excitation response are captured in one sample interval of the FFT. For the sine chirp excitation, this is the burst random. This is sine chirps of each contents. The repetition of the signal over the sample interval satisfies the periodicity requirement of the process. While other excitation signals also exist, these are most common excitations. So Some more we'll talk a bit later on. Tell me more about windows. This is pretty important. Again, okay, he elaborates on that. I'm not going to go through all that again. And let's talk about the flat top window. Okay, he talks about flat top, force exponential window. He repeats things like that, which are used. Plate mode shapes for mode 1. Peak picked FRF. So how it is doing for getting mode 1, it's picking the data for mode 1 only here, mode 1, this deflection negative, negative, down, if you see the center and up, down, and at this point 4, the imaginary component showed up, and this showed negative here, that's it. For 6 points, a rough approximation is showing you what mode 1 is, okay? For mode 2, then he goes to the second frequency here. And second frequency he picks for everyone, waterfall fit. Okay, for point 1, up positive. You see that? Second is negative. You see that? Negative. Then third point is 0. You see here? At this point, you don't see anything. So it's a 0 point. There's no movement there. Fourth point is also 0. There's a resonant peak there, but the amplitude of it is 0 because it's a node point. Then fifth point is negative down, sixth point is positive up. You got the twisting mode. Plate mode should peak, but simply peak of a part of data you generated. And all other points, just give you the example, hence gave you that. But all other things, if you fit full, if you have a powerful system, time available and all that, any complex thing can be generated. How do I get the mode shapes from the plate FRF? So now that we have discussed various aspects, 6 possible places, whatever I described over here just now, that's what is there. Software to simplify the extraction process. It's so powerful that all this data is gathered, and be careful that you define very clearly what is the direction of movement and all that, right in the upfront, plus, minus, and left, impact hammer direction, all those, the software guides you into giving the correct directions and all that. The basic parameters that are extracted from the measurements are the frequency, the damping, and the mode shapes, dynamic characteristics. The measured frequency response function is basically broken down into many single degree of freedom systems. You see, like here, it breaks it up. These curve fitting techniques use a variety of different methods to extract data. Some techniques employ time domain data, while others use frequency domain data. The most common methods employ multiple analytical models, but at times very simple single methods will produce reasonably. There are lots of curve fitting routines, the exotic ones and all that which can do, but best is as if identify each. See, the total one consists of first mode, the second mode, and third mode combination will show you like that. So everywhere else, there's a combination of all these things. But at resonance of this, the fundamental mode picks up, the mother mode's components are less. At this peak, the other components are less, this is down, like that. So each complex mode is taken, if there are two close by, you do a curve fitting algorithm using a single degree of model by zooming there and picking the data and getting the data. But if you define to your software, there are two modes and you have to pick, it will do a multi-degree of freedom curve fitting algorithm, which distinguishes between these. These are called closely coupled modes. A bending and a twisting mode may be very, very close together at a very close frequency. All structures respond to externally applied forces, but many times the forces are not known or cannot be measured easily. We could still measure the response of a structural system even though the forces may not be measured. You're not measuring, you're already giving it and doing it. So the next question is, important thing is what's called operating data. Now, in modal analysis and operating deflection tapes are two different things, okay? What are operating data? We first need to recognize that the system responds to the forces that are applied to the system, whether or not I can measure them. So for explanation purposes, let's assume for now that we know what the forces are. While the forces are actually applied in the time domain, there are some important mathematical advantages to describe the forces in response in the frequency domain. For a structure which is exposed to an arbitrary input excitation, the response can be computed using the frequency response function multiplied by the input forcing function. This is simply shown in figure 24. Okay, input spectrum, frequency response spectrum, output spectrum, input time force, output time force, schematic view of what's going on. Okay, in all these. So that simple plate that we just discussed, let's assume there is some operating condition that exists for the system. A fixed frequency operating unbalance will be considered for the excitation. It seems reasonable to use the same set of accelerometers that were used in the plate. If we acquire the data, we may see something that looks like figure 25. Suppose you wanted to just measure at some frequency, you will see the plate pattern from that accelerometer, something like that. This is the measured operating displacements based on the accelerometers that were used to pick up. Looking at the deformation, it's not very clear why the structure responds this way or what to do to change the response. Why does the plate behave in such a complicated fashion anyway? This doesn't appear to be anything like any of the mode shapes that we measured before. Very clean cut. You see these modes? Very clean. Why? Because in order to understand this, let's take the plate and apply a simple sinusoidal input at one corner of the plate. Okay? And apply a simple sinusoidal. For the example here, we are only going to consider the response, assuming that there are only two modes for starters, that they are activated by the input excitation. Of course, there are more modes, but let's keep it simple to start. Now we realize that the key to determining the response is the frequency response function between the input and output. Also, we need to remember that when we collect operating data, we don't measure the input force on the system. We don't measure the system frequency response function. We only measure the response of the system with some accelerometer. So first, let's excite the system with a sinusoid that is right at the first natural frequency. Okay? If we hit it, that is right, mode 1. The mode 2 contribution, you see this fellow, is a little bit. Okay? These two are put together and mode. So even though we excite the system at only one frequency, we know that the frequency response is the filter that determines how the structure will respond. We can see that the frequency response function is made up of a contribution of both mode 1 and mode 2. We can also see that the majority of the response, whether it be in the time or frequency, is dominated by mode 1 at this resonance. You see that? Now, if you want to measure the response only at that one frequency and measure the response at many points on the structure, then the operating deflection pattern would very much look like mode 1, but there is a little small contribution to mode 2. Remember that with operating data, we never measure the force or the frequency. We are only measuring the output response, so that the deformations that are measured are the actual response of the structure due to whatever excitation, whatever it may be. Now we measure frequency response function, estimate modal parameters. We actually determine the contributions of all these and all that. Notice with operating data, we only look at the response at one particular frequency, which is the linear combination of all the modes that contribute mixture. So we can now see that the operating deflection pattern will look very much like the first mode shape because we are very much close to that. It will look like that. Okay. Now, again, we must realize that the response looks like mode 2, but there is a small contribution of mode 1. What happens when we excite the system away now close to? Suppose we excite the structure here, away from mode 1 or mode 2. So there is a little bit of combination of this. There's a little bit of combination of this, and which means a little bit of combination of mode 1 is this, a little bit of combination of mode 2 is this. So if you add all the data points on this, well, this is what is general shape. Any other point is a general disturbance like this, general pattern, and so on and so forth. If you now again excite here, the mode 2 contribution will be more, mode less, and then the clear, nice, neat, resonant pattern. So any other part on the structure force, if you operate at those frequencies, you see a general disturbance. But like we saw for the bell when we started off this whole lecture series, it's a combination of all the series put together, mode shapes with form. That's what is called an operating deflection tape. That's the mid-range between mode. Now here is where we see the real difference between modal data, operating data. Figure 28 shows you what is the difference between those two, okay? But if we look at the deformation lot long enough, we can actually see a little bit of first bending mode and a little bit of first torsion mode in the deformation. So operating data are primarily some combination of the first and second mode shape. There are other modes also, remember, but we are focusing on first and second one. Now we have discussed all of this by understanding the frequency response function contribution of a mode by mode basis. When we actually collect operating data, we don't collect frequency response functions, but rather we collect output spectrums. If we looked at those, it would not have been very clear as to why the operating data looked like mode shapes. Figure 29, where that shows a resulting output spectrum. Before that would be measured at one location, now the input applied, but by understanding how each of the modes. So actually there's a big difference between operating deflections. ODS is a big study. ODS, they study the actual deflection patterns on moving structures and all that to get a general idea, and they separate it. Then they go in for a modal analysis to do all this. We can now see that the mode shapes are summoned together in some linear fashion to form the operating deflection patterns. But typically, we are interested in the total deformation on response structure. Why do I even want to bother to collect modal data? It seems like a lot of work to acquire. So there are some things to do. So what good are modal data? Modal data is different from operating different. They're extremely useful information that assist in the design of almost any structure. If you want a design characteristic, you need modal data. The understanding and visualization of mode shapes is invaluable in the design process. It helps to identify areas of weakness in the design or areas where improvement is needed. The development of a modal model based on this data is useful for simulation and design studies. Remember, Tejas and Dr. Ravi Prasad showed you some simulations and all that. Well, to do that, you got to acquire some of these in this. This is a mathematical process which uses modal data, all these frequency damping, to determine the effects of changes in the system characteristics due to fictional structural changes. These calculations can be performed without actually, once you get and verify for a particular data, that frequency damping and modeling for a structure, verifying from that point, you can go on, simulating softwares and all that you can put and do what is called structural dynamic modifications, making a change in the mass, how would it affect things like that. So determine the effects of changes in system. These calculations can be performed without actually having to physically modify the structure until a suitable set of design is achieved. So it is very powerful. Schematic of this process is shown over here. You take that modal data, schematic of the SDM, structural dynamic modification, experimental modal testing. You get modal parameters, finite element model, eigen solution, develop the modal matter, make some structural requirements. Yes, use the structural dynamic to evaluate changes. Repeat until you get those. See a mass change, a rib stiffener adding, a dashboard adding here, spring adding here. All these changes can be done theoretically with a verified model, and afterwards you can build all these things and verify back. Okay, frequency response measurements, corrections, overall dynamic model process. We'll come talk about it more towards the later part of the course. Rib stiffness, mass, model characteristics. So operating data, on the other hand, is an actual depiction of how the structure behaves in service. This is extremely useful information. However, many times the operating shapes are confusing and do not necessarily provide clear guidance as to how to solve or correct an operating problem, and modification response tools cannot be utilized in operating data. So you will see in the fields of ODS, operation, deflection, shapes, and all that, and operating data collected. And it has its relevance because it's a combination of those to actually see how the overall behavior here is. So the best situation exists when both operating data and modal data are used in conjunction to solve structural dynamic problems. So basically, folks, it says some simple explanations were used to describe structural vibration and the use of some of the available tools for the solution of structural dynamic problems. This was all achieved without the use of any detailed mathematical relationships. We already saw those in math, matrix forms and all that, how mathematically you manipulate the data to generate a frequency response function by generating a mass matrix, a stiffness matrix, and a damping matrix, and doing the inverse, the transform, the Fourier and all that as a lumped system. But as a continuous system, you already generated all that information by experimentally and validated the same thing. You take the finite element model, those who sit good at computers sit on, go on doing those without having realistic knowledge of what's happening. I always was very much, amazed at these kids who come and sit and in front of the computer and see and not knowing half the time what they're doing. They're just varying the changes and all that and anything. No, I want them theoreticians. That's why when I did my PhD too, apart from experimental, I had to do some finite element modeling to see the difference between that and that. And later on, you focus on one area or the other. But sometimes finite element guys do a lot of things without realistically knowing what's going on. So, in order to better understand more of the details of the data presented, a theoretical treatment is necessary. So a theoretical treatment was what we started with, okay, and we tried that with this over here. So I believe again that please go through it. Please go through the article, some of the explanations and all that. And if you have any questions right now, or even I would encourage reading it before asking questions, like I do to my own students, because some of the things they have are already answered there. I'll be very gladly be willing to answer those. Then again, this is just one article. If you want more and more details on each and every one of these, which is asking, he's covered those in at least, I believe, about 15 or 20 sub-articles, given more depth. I have few of them which I'll be using in my lectures tomorrow and after to emphasize certain points. Not all of them. I don't have the time to do all those. But then again, I hope that, at this point, you guys have an overall good picture of the concept of modal analysis. Next 2 days and all that, we'll go through some more in depth of windowing functions and this and that to elaborate and things like that to make clear. Then I will show you some of my case studies that we have using these experiments and all that. And on day 5, I have what research is going on blast and impact, and using these vibration experiments to characterize and materials, damping in materials, and how to distinguish how improvements in damping and all that. And the last day, which uses some of these techniques that we talked about over here and all that. So I believe it's almost 11:30 here, which is 11 o'clock there. Tej, we are in time to close
Yes,
for the
sir.
day.
3 more minutes to 11:55.
Okay.
Sorry,
If anybody has a
10:55. It
question
is
or two,
10:52, sir.
Any questions?
if
Yeah,
anybody
we
has
can
a
engage
good
now.
question, I can answer. If not, I can still. I would like them to read first, like I do. Do you remember, Tej, my students?
Sir,
You got
Professor Mantha, I have a couple of questions, sir. Can I ask?
Yes. Yes, go ahead.
Yeah, while carrying out impact testing,
Hmm.
what is the best place to fix the accelerometer? Any
Okay.
point we can keep, or suppose if we take a simple beam or cantilever beam,
Okay.
so where do we have to fix the accelerometer?
Okay, that's a good question. As a simple action, let me go to the beam over here if they have, okay. Ideally, if you have some background in vibrations, you will have some knowledge about what the nodal mode patterns are. Okay, it's a good it's difficult to understand the modal patterns on plates and all that, but at least a beam will have Suppose you have some idea about the modal pattern, you don't want to go too much into this. Ideally, it would be great to come not here. This is not ideal because sometimes the deflections are not much. You need a larger bang and all that to get some output out. So somewhere more towards the tip end. Even that is dangerous because as you go on tapping here, the thing will trigger as a larger one. So not over way back at the tip, but somewhere in this region would be ideal, but not a node point like over here. You see that? You'll miss that node. Or if you put somewhere over here in the center, the third node will be gone. You see that over here? Because that's a node point for that. So you have to have some idea. I would not recommend near the base, towards the end, as much as away so that you know you're not near the mode, you're not near the fag end either. Okay. Now, if it comes to a plate and things like that, don't ever put your accelerometer on the lines of symmetry. You see the lines of symmetry, the center lines and all that, because always those lines become for some mode or the other, they will become a nodal line.
Node.
Okay. For any structure where there are lines of symmetry, two-dimensional I'm talking, as opposed to the beam you talked about. You don't want to put your accelerometer along that. So any other portion away, like towards the region of larger deflection, like the tip ends and all that, would be ideal.
So some sort
But
of
watch
basic
out for the
idea
fact
of mode pattern, mode shape should be there to fix up.
yeah, some rough knowledge.
Some rough
Well,
knowledge, yeah.
what
Otherwise,
is
yeah.
likely to be the modal pattern and all that would help. If not, you can put it and do it at the driving point measurement one and see whether you're able to capture all that. Suppose you had put an accelerometer over here and you try to do a driving point measurement, you'll miss that mode over there. Okay. So you'll know something. So try to move the accelerometer this way, that way, and see whether driving point measurements will take. Then you'll know that as many of the peaks are showing up, then that's the best point.
Okay, sir. Thank you, sir. That is very much informative because those who are carrying out the experiment first time, so,
Yeah.
so somewhere in case of symmetry, suppose normally they may keep somewhere at the node of a mode, so we won't get, we cannot extract all the modes of interest, right?
No. You got to, you have to make some trial runs. You can't just arbitrarily put away because exactly like in this example, you see that?
Yeah.
If you put there, you impacted there, and you know he lost it. Okay, that particular mode impacting there itself or picking the response itself, that won't show up on the spectrum over there. You're lost.
Yes.
That signal is lost over here. You see?
Yes, sir.
The signal is lost over here and here and here.
Yeah. So, and one more question, sir, a fundamental question I have. Say, there was in the history, there was one example, I think you might have heard, a Tacoma Narrow Bridge in USA, which is collapsed after left it for operation within 4 months. Why? Because in one fine day, strong winds have blown at not that much strong, but at a speed of 60 kilometers per hour. But the forcing frequency coincides with one of the natural frequencies of the bridge, and the bridge has suffered more torsional displacements. So therefore, that has been collapsed. So
Yes.
my point is, if you take a structure or a machine, they are already built up. Okay. So how do you avoid the resonance in such situations? Because we cannot do anything. So a machine at operating condition or structure which is in its operating condition, if they suffer large like displacements because of resonance, so how do we minimize
Damper.
effects of
Damper. The role of the damper is, if you cannot avoid that, you build in the damper to be to reduce those amplitudes at resonant conditions to acceptable levels. That's the only role of the damper. It does not change the frequency. It does not, modal pattern will not change, but at least the amplitudes are reduced to reasonable levels.
Okay, so that's good. Because we
But
cannot
again, it's
change
not
the
a good
mass, we
idea
cannot
to keep-
change the stiffness. Yeah.
Yeah, you can do those if the mass of the machine normally cannot be changed. You can
Yes.
change the stiffness to move away from the resident conditions. Yeah, those should always be the first attempts. Okay, change the stiffness or lower or increase the mass to change the resident condition. That should be always, if allowed, if feasible. Sometimes removing material from a turbo generator is not possible, right?
Yes, sir.
You can add mass if you like,
Yeah.
but not remove. Or
Yes. Yes.
you can change the stiffness to make softer springs and things. Always those should be there. But if it's unavoidable, like I always say, for my turbines and generators in BHL, when we start up from zero to reach the operating conditions, there's always a region where you may have to pass through the natural frequency of the whole mass. So since you have to pass through, you will incorporate certain dampers into it, so that at that part, when it is at that, even for momentarily, the response is not instantaneous and infinity, but it's a little bit of finite movement which is allowed with tolerances, allowances, and then it passes away. So the goal in the frequency is either build the machinery in such a way you're below resonance, or build it to be in the above resonance region. Okay, by varying the parameters of natural frequency. Omega 0 forcing by omega f n. Omega n is square root of k over m in a simplified form. I'm talking about k equivalent by m equivalent. So design it to be in the low range or design it to be. But if it cannot be avoided and you have to pass through, then damping is the only way which will curtail into which is.
Sir, anything, I think, can you elaborate maybe in the coming lectures regarding ODS and its measurement?
Which measurement?
ODS, operating deflection shapes.
Deflection.
Oh, operating deflection shapes.
Yes.
Yeah.
I don't know whether I have some of that. Maybe some of the lectures that Peter Avitable has more in this. I'll send you some notes. Operating deflection shapes.
Yes, sir.
If I have some, I'll pick it up. Okay.
Okay, sir. That's all from my side. Any questions from participant side? Otherwise, we'll close this session and we have the next session like laboratory testing using impact and laboratory experimentation using impact hammer. We have positive at 11:30. Any questions? So, okay. So, Tezeswi, shall we close? Stop the session now?
Yes, sir. Thank you so much, Professor Mantena, for the insightful session.
Yeah, encourage the students and tell them that your test questions will be something like this. Okay, then they'll start reading. Okay.
Definitely, sir.
Okay. All right.
Thank you, sir. Thank you very
Thank you,
much.
sir.
Very
Good night.
informative, very helpful lecture.
Okay. Well, my students find it very helpful, so I'm sure anybody who goes through this will like it. I'm sure it's been a good way that it is put together.
Participants,
Okay.
yeah.
All right.
Yeah, we will send this copy. First of all, just go through what Professor Mantana repeated 3-4 times. All of you should go through this paper which is shown to get complete picture of what is experimental model analysis. Okay, so I think that would help you a lot. Okay, while coming to the next lecture, if you go through this and I think you will come with some doubts. I hope. Thank you, sir. Thank you very much. Now I am
Okay.
recording.
All right.
And
Tomorrow again, 8:30, right? Same 8 time,
Yes,
8
sir.
o'clock. Okay.
Yeah, IST 8
Sir.
o'clock.
Okay. All right, Tej. All right,
Thank you.
Dr.
Good night.
Prasad. Bye.
Good night.
Thank you.
Yeah.
So now we have the break and we'll meet at 11:30.
Yeah.
Right.
Thank you. Good day.
Thank you, sir.
Hello? Able to hear me?
You are audible, sir.
Yes, sir.
Yeah. So welcome to this lab demo session. We try to like make you as interactive as possible. Okay. First of all, I'll give you start the record. Yeah, welcome to this demo session. First of all, initially, I will just give you a quick review of what is impact testing, 15 to 20 minutes. I'll just show you instrumentation required for this impact testing. Just set up everything and then we will go with the live demo. Okay. Now, I'm sharing my screen. Please let me know. Able to see this. Able to see my screen?
Yes, sir. Yes, sir. We can see the screen.
Yeah, Professor Mantana has covered almost the theoretical concepts of model analysis, impact testing using impact hammer, also Shaker testing. Background theory is both is same for both impact testing as well as Shaker testing. Okay, using impact hammer testing, we'll get measurements in the form of a row, whereas in the Shaker test, we'll get the measurements in a tall. That is the only difference. So of course, at the end of this course, you'll come to know. Okay, so what is the basic difference between impact testing and Shaker testing? Yeah, as you know that model analysis is a process of describing the structure in terms of its dynamic characteristics or model parameters such as natural frequency, damping, and motion. Okay, as you know that natural frequency is the frequency with which structure vibrates, and mode shape is the pattern of vibration of a vibrating system. Come to know how the structure will vibrate the given input excitation. Damping is the process of release of vibrational energy. There are different forms of damping. Of course, that part has been covered. Only basic definition I am just giving you to recollect the things what we have discussed in the past couple of days. Now, why model analysis? Why it is important? Why a lot of popularity gaining all over the world for this model analysis? So, by doing this model analysis, engineers should design the better structures, can design the better structures. How they can design the better structures by identifying the natural frequencies, how they might affect the response of the structure when a force excites the structure. And also understanding the mode shapes, how the structure will vibrate when excited helps the design engineer to design better structures. And also model parameters are required to avoid resonance in structures which are affected by the external periodic dynamic loads. That is very, very important. In the previous session, I highlighted one example, the Tacoma Narrow Bridge in USA, which is collapsed after left for operation within 4 months. So because of this resonant condition, we find a strong winds have blown at a speed of 60 kilometers per hour. Of course, the winds are not that much strong, but what happened is the frequency of the winds coincides with one of the natural frequencies of the bridge. So therefore, resonance has occurred. So torsion modes had played a role there, and the bridge has been collapsed because of this resonant condition. That should be avoided with respect to civil and mechanical engineering systems are concerned. Another important parameter nowadays, most of the researchers concentrating on health monitoring of structures. In that point of view, the change of model parameters directly provides an indication of structural damages based on the changes in frequencies and mode shapes of vibration. So we can correlate the change in model parameter with the damage, extent of damage that has been occurred. So therefore, we can also use these model parameters for the health monitoring of mechanical systems. Okay, mechanical system in the sense, don't think that they are with respect to mechanical engineering. System which consists of mass, stiffness, and damping. Okay, now coming to the application, of course, we were mentioning applications are there in civil engineering systems, mechanical engineering systems, aerospace applications, spacecraft applications, biomedical engineering, and the list just goes on and on. Yeah, now coming to the impact hammer testing. So this is the test setup, schematic diagram of test setup. So if you take a simple beam, so it is supported two locations. So this is the impact hammer. This is the impact hammer. Accelerometer is fixed at one of the location. You can see here. And both impact hammer and accelerometer connected to the dynamic analyzer. This is FFT dynamic analyzer. This is the data logger. So all the measurements finally come to this data logger, and softwares are loaded here, model analysis softwares. So from that, we will get from the measurements, we will get frequency response function, and correlating of that frequency response function, we will get the dynamic characteristics such as natural frequency, damping, and mode shape. Okay, so now what is this impact hammer test? It is so popular and convenient technique for carrying out the experiments. Very fast. Few averages are required to avoid the statistical error in the measurements, like 3 to 5 measurements. Mentioned that. So 3 to 5 measurements are sufficient, and the energy is transmitted to the structure in very short period of time, just impulse. Okay, so therefore, the shape of the force signal depends upon the hammer tip, mass of the hammer. There are different tips. Okay, we have to identify which tip is best suited to carry out experiment with this impact hammer. So based on the surface hardness or based on the mass of the member to be tested. If the tip is stiffer, shorter will be the force signal. The shorter will be the force signal. There will be wide frequency range. Okay, so we can get more modes of interest with stiffer tip. Sometimes we'll add extra mass to the hammer, which will widen the force signal, but that will lower the frequency. Of course, this is very hand equipment and we can easily use in the field also. Yeah, this is the impact hammer, the hammer what we have in our laboratory. The model of this is PCB make, and the model is 086D05. The sensitivity of this hammer is 0.23 millivolts per Newton, and weight of the hammer is 320 grams. And there is a provision here to extend the weight of this hammer. We can that thread provision is given. If required, we can add some extra mass to this hammer also. Yeah, now that hammer is fitted with the force transducer. So there is a force transducer here. Okay, so that will be used to measure how much of force we are applying to the test system. So different tips are used based on the frequency range of interest. So hard steel tip for higher frequency range. In that case, the pulse duration is very short, but we can get more frequency range. So in case of medium hard, like plastic and Teflon, so this is the pulse of that you can see here. And in case of soft rubber tip, used for low frequency measurements, and broader is the pulse, but frequency range is less. These are the different tips you can see. This is the soft rubber tip. This is medium plastic tip, steel tip with some cap, So if required, sometimes if you think that the tip is so hard, so you can use this rubber cap to the tip. And this is the extended mass. So sometimes to excite the structure, if you feel that the hammer weight is not sufficient, so we will add this extra mass to the hammer. These are the different types of tips we can see here. Yeah, coming to the, as I mentioned, a impact hammer fitted with a force transducer at the tip. So therefore, what is force transducer? It is a simplest type of piezoelectric transducer. If you see the cross section of this force transducer, see, these are the piezoelectric crystals, so which are placed between the casing of this transducer. When a force, a fraction of it, is applied directly when we are hitting the structure, what happens? Force will be applied to these crystals, piezoelectric crystals. They will generate a charge which is proportional to the force that is applied. So that signal will be generated from these piezoelectric crystals. Now this is the accelerometer. You can see this is the accelerometer, and this is the schematic view of this accelerometer, and this is the cross section. So this is widely used vibration measurement. So when accelerometer vibrates, the internal mass, this is the internal mass, okay, which will apply a force to the crystal, which is proportional to the acceleration. When we are hitting the structure, what happens? The structure will vibrate, the member will vibrate. So along with that, this accelerometer will vibrate. So when the accelerometer is vibrating, this spring-loaded mass will press these crystals, and based on the acceleration of vibration, the charge will be generated. Okay, so this will be sent as a signal. This we are going to measure. What is the main advantage of this piezoelectric accelerometer is this is very small, compact, having low weight, high sensitivity, and high frequency range. Okay, so suppose you are using accelerometer. Suppose if you want to get the response in terms of velocity, displacement, there is a well-established relation between those three parameters. We can obtain them easily. Yeah, these are the accelerometers. Diatron make accelerometers. We have. So Diatron make USA, and PCB make accelerometers also that are available. The model here we use is Diatron 3055V2. The sensitivity of this accelerometer is 100 millivolts per gram. Weight of this is very, very small weight, as Professor Manthana mentioned that. So the weight, sensor should not add more weight to the structure to be tested. Okay, so this influence should not be there on the structure. Therefore, this is very less weight and very sensitive. And you can see in animation, when a mass is spring-loaded mass pressed the piezoelectric crystals, a charge will be generated that will come in terms of voltage. So that signal we are going to capture using this FFT analyzer. Now coming to the heart of this model analysis is dynamic analyzer. These are the different analyzers you can see. These are the analyzers. The main component of this impact hammer testing is analyzer. There are different types of analyzers, 4 channel, 8 channel, 16 channel, 32 channel, like that, different types of analyzers. Here what we have is 8 channel Varus dynamic analyzer. Okay, so we can get simultaneously 8 different measurements, right? So what this analyzer will do, if you look at quickly what this analyzer will do. Initially, analyzer will filter the signals, okay, and any overloading of signals that are there, analyzer will filter them. Whatever range we are interested, we'll get those signals. And after that, the analyzer will convert the signals from analog to digital. So from the measuring devices, from the impact hammer and accelerometer, we will get the analog signal. those analog signals which are in time domain, they will be converted into digital signals. Analog signal is a continuous signal, and digital signal is a discrete signal. Okay, so that ADC will be done by this analyzer. Next, another important, just now half an hour back we have seen windowing. So this is very, very important for the measurement of this, to get the measurements. Windowing of signals. Force window will be applied to remove the noise in the input signal. An exponential window will be applied to the response signal to prevent the leakage of the signal. So entire response we are supposed to capture. Okay, there should not be any leakage. To avoid that, we have to apply this exponential window to the response signal. And then conversion of signals from time domain to frequency domain using fast Fourier transformation. Okay, that will be done. It's a mathematical expression. Of course, all these functionings will be done by this analyzer. So this is the data logging PCR workstation. So all the measurements finally will come to this, will be stored here, and these laptop or PC, whatever it may be, they are loaded with the model analysis softwares. Here you can see the like channels, different channels. So one channel we have to fix hammer, impact hammer, and at the other channel we have to fix accelerometer. Of course, we'll show you these things, just set up everything in a live demo. So what is the purpose of this softwares? What we do, we have to create the geometry, then we'll do the curve fitting of the FRFs. From the curve fitted FRFs, we will get model parameters such as natural frequency, damping, and mode shapes. Okay, now this is model analysis software key. We have to use this dongle. Yeah, how do we determine the dynamic characteristics using impact hammer? Steps which are there. So dynamic characteristics can be obtained from the set of measured frequency response function. So we will measure the frequency response function between input force and output response. So the frequency response function is a fundamental measurement that isolates the inherent dynamic characteristics of the structure. This is very, very important measurement. So therefore, FRF is a measure of how much displacement, velocity, or acceleration response the structure has at an output of the given input excitation. It describes the input-output relationship between 2 points on a structure as a function of frequency. If you look at the FRF model, so here we are giving the input force, and then here we will get the response. And this is the transfer function. So that is, which is nothing but a ratio of output response to the input force. Mathematically, FRF is defined as the ratio of Fourier transform of output response to the input force. So different ways of representing the frequency response function based on the output measurement. If you measure the acceleration response, then the FRF is called as receptance, acceleration by force. Okay, and its inverse is force by acceleration, that is effective mass. And if you measure the response in terms of velocity, then the FRF is called as mobility, velocity by force. Okay, and its inverse is impedance, inverse of this, force by velocity, which is called as impedance. If you measure the displacement as a response, then the displacement by force is called as dynamic compliance, and its inverse is called as dynamic stiffness. There are different ways of representing frequency response function in terms of receptance, in terms of mobility, in terms of dynamic. Yeah, this is the typical frequency response function These are the peaks we are interested in. Okay, these peaks will represent a resonant condition, and the frequency corresponding to these peaks will give you the resonant frequencies, resonant natural frequencies of the system. Above you can see there is one line. See here. Okay, this is called as coherence. This is very, very important function we have to look at while carrying out the experiment, because we have to look at the coherence, which will indicates how quality output measurement we are getting for the given input force. Okay, so the coherence should not be less than 90% for any measurements. Okay, 90 to 100%. 100% means 1. 90% means 0.9. So while carrying out the experiments, we have to look at this coherence function, which indicates the quality of output the given input excitation. That should not be less than 0.9 in any valid measurement. So if less than 90% means the signal is not good, there is some disturbance, we have to discard that measurement. Yeah, now how do we estimate the model parameters? Model parameters are most commonly identified by curve fitting the set of frequency response functions. We have seen in the previous slide, yeah, this is the frequency response function. By curve fitting this FRF using model analysis software, we can identify the dynamic characteristics. What is curve fitting? It is a process of matching a mathematical expression, the set of empirical data points. It's a process of matching the mathematical expression to the FRF. So with that, we will get a dynamic characteristics. There are different curve fitting methods: SDOF method, MDOF method. Okay, in the SDOF method, we'll consider each peak separately and then we combine. So in the MDOF method, all the peaks of frequency response function considered at a time. Now, what are the general steps involved in carrying out this, in obtaining these dynamic characteristics using impact hammer test? So first of all, we have to mark the excitation points on the surface of the test beam or plate, whatever it may be. Okay, test beam or plate or anything, any object. How many points we are interested to get the measurements, we have to decide, and then we have to mark the excitation points on the surface of the beam. And then we have to create the geometry of the test structure based on the excitation points selected in the model analysis software. Then we have to give various connections, like connection from impact hammer to the analyzer, from accelerometer to the analyzer, fixing accelerometer to the specimen, and then from analyzer to data logging facility. Everything, all the connections we're supposed to give. And then we will measure the FRF by exciting the structure at one of the points, excitation points. Then we will get the response from the accelerometer, which is fixed at some other point. And then after obtaining FRFs, we will curve fit the frequency response functions, and then we will get the model parameters. And after curve fitting, we can also obtain display. We can also obtain the mode shapes of the test beam or plate structure, whatever it may be. Okay. Yeah, this is the schematic diagram you can see here. Yeah, this is the typical screenshot while carrying out the test. Yeah, these four are very, very important. You have to look at. So this screen, this will indicate the force signal in the form of a pulse. Earlier, just now we have seen, using different types of tips, different pulse shape would be different. So using hard tip, the pulse duration is small, but high frequency range will be there. So this is the force signal we have to look at. This is the response which is obtained from the accelerometer we have to look at. And this is coherence. We have to, in this window, we can observe the coherence function Here you can see the coherence is, in this case, it is 99%. So this should not be less than 90% under any circumstance. And this is the frequency response function which is obtained for the given input excitation and for the output which is obtained from the accelerometer. Okay, this is typically on the screen. While carrying out the test, we have to look at these four, right? Four signal response from the accelerometer, coherence function, that is between output response and the input force, and frequency response function, which is the ratio of output response to the input force. This is the FRF before curve fitting. Okay. Yeah, whatever measurements that we are obtaining using like the analyzer, what we have here, all the measurements that will come with the AE2 format, extension AE2, and then we have to convert them into universal file format, UFF. We'll use another software like to the conversion from AE2 to UFF. Okay, so once you converted all the measurements to UFF format, and model analysis software can recognize those measurements. So this is how the geometry is created. This is the geometry of the beam what we tested here. So there are total 33 excitation points we have marked here. So one line there are 11 points, in 12 to 22, 30, 23 to 33. Total 33 excitation points we have while testing this. Okay, so we have created the geometry of the test surface in the model analysis software. Initially, we will create the nodes, then we join these nodes. Okay, the closing is there. Yeah, this is the FRF after. This is the frequency response function which is obtained after testing. That is the first mode. Of course, these things will show you. This is third mode by bringing the analyzer cursor over the peaks. This is the first mode frequency, second mode frequency, third mode frequency, like that. You will obtain different different modes associated with these peak frequencies. Yeah, another important parameter, model damping. So damping is nothing but this is the process of release of vibrational energy. This is where sometimes it is required, sometimes it is not required. Depends upon the application. So using a frequency analyzer, it is to identify the half power points of the magnitude of the frequency response function. The damping is measured in terms of using half power bandwidth, as Professor Mantana mentioned. So if you take any peak, 3 decibel down, this is the resonant frequency, 3 decibel down. Okay, identify the points on either side. So then this is omega 1, this is omega 2. So omega 2 minus omega 1 by 2 omega r will give you damping. Okay. So what are the applications of this impact hammer testing? The purpose of our vibration testing. The purpose of vibration test is to identify the dynamic characteristics of the structure by measuring its response to the dynamic force caused by the operational conditions or man-made vibrations. So if you take a bridge, there are vibrations in the bridge due to vehicular movement. Similarly, with respect to any machine, when it is working, there are vibrations. So in the context of structural health monitoring, changes in the vibration characteristics can provide useful information with respect to the condition of the structure. Use of this information to identify the damage, so which is also called as vibration based damage detection technique, which is an NDT technique. So in this test, strategic Hello. Are you able to see the screen which is projected to the laptop?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, now we are going to show you the demo. So the test setup and everything, that is the data logger. Then can see this is the analyzer, dynamic analyzer, Walrus analyzer. The photographs what I have shown in the PPT, same thing. Channels you can see there, 8-channel Walrus dynamic analyzer. Okay, initially there is a connection between the analyzer and the data logger. Between the computer, you can see here that white wire through PCMCI slot. Of course, this is old equipment. So the interface is between the analyzer and data logger is through PCMCI. Okay. Next, moving on. So this is the analyzer, and there are two channels you can see there. One wire is connected to channel 1, and that is for the impact hammer. Another one is for channel 2, that is for the accelerometer. You can see here we have a simple test setup we made. Moving on, this is the prism what we are going to test, which is 500 mm by 100 mm by 100 mm, which is supported on flexible supports, rubber supports. You can see the supports, two blacks, you can see them. So these are the supports. And impact hammer you can see there. Okay, so at the tip impact hammer, the tip force transducer is fitted, and the accelerometer you can see there. That is the accelerometer which is placed at node number 11. Here the entire surface has been divided into total 18 18 excitation points on the surface you can see. So now the accelerometer is placed at one of the nodes, one of the excitation points. So what we do is we will hit at all the excitation points 1, 2, 3, 4, and then 5, 6, 7, 8, 9 till we reach the 18th point, and we will pick up the response from the accelerometer which is placed at one of the excitation points. Okay, so total 18 measurements we will get, total 18 different FRFs. And another important point Professor Mantra mentioned is driving point FRF, which is nothing but we will hit at the point where we place the accelerometer, that is at node number or excitation point number 11. Okay, so there we'll get driving point FRFs. It's a typical FRF which consists of sharp peaks. Okay, and then directly anti peaks will come there from that. So those FRFs, of course, we can see. This is the simple test setup for a small beam. Same thing you can made in case of a plate. You can use C clamps to fix to create the fixity at one side, and the other side it can be free. Okay, but as we were discussing in the morning, we are supposed to have some basic idea where to keep the accelerometer. One dangerous thing is if you keep the accelerometer at the node of a mode, then you won't get response. Okay, that is so some basic idea of vibrational modes, whether it is a beam or it is a plate or anything. So that we have to look at, and then we have to identify the location of the accelerometer so that we could be able to capture all the modes of interest. That is the primary thing we have to look at. Okay, now we will see. We'll start with giving input parameters in the software, Walrus Analyzer software, which is loaded in this laptop. One by one, step by step, we will go, and we will show you the demo. Of course, you people may have, some of you may have with different softwares and different, of course, instruments. But here, what we are having is Walrus Analyzer and NV Solutions Model Analysis software. Okay, now we will open the model analysis like Walrus software to give the input settings. Okay, please bear with us because the screen may not be that much big. Okay, we'll see as zoom as possible. Okay, so now it is opened. We have to create a new project by clicking on new project. Then click OK. Then here we have to give the project name. So this is very, very important. Whatever name you are giving, you have to remember there is a specific purpose for this. I will tell you later. Give the name of the project. Let us give demo. Demo. And then select the drive where you are storing these measurements. Here it is D drive or any location. You can select. And also you can select the folder where you are going to store these results, and also you can give comment in the description box. So description box, you can give the comment like dynamic testing of SSB. Any comment, anything in future reference. Suppose what is this measurement consists? You can give some information. Okay, dynamic testing of simply supported beam like that, and then click on next. Click on next. So here we have to give sub project name, and then same title we are giving here, project, sub project, measurement, everything same. Demo, that is with case sensitive, we have to remember. Okay, click on next. Click on next. Okay, now input parameters. Here there is channel 1 and channel 2. What is channel 1? Channel 1 is for impact hammer. Channel 2 is for accelerometer. Okay, channel 1. So we have to give the range, frequency range. That will be 310 millivolts, and click on ICP. We have to check whether the connection is proper or not. We have to check whether the connection is proper or not. So therefore, to get the valid measurement. Okay. Now you can see here. Green color is lit up. So our connection for channel 1 is good. Then, okay, click on channel 2. And then in the channel 1, we have to select the type of transducer we used. So, and also type of measurement we are getting. We have to select force there because channel 1 is meant for force. Channel 2, force and model we have to give. 086D05. This is the model of the hammer what we are using. Then go to channel 2. Channel 2, here we have to give range, voltage range 100 millivolts. We'll give. Then ICP coupling. Then check ICP. This is very, very important step. What happens is, if we have to get the green signal here, we get red signal or something, means that will indicate like open circuit or short circuit. If it is open circuit, the connections are not good. Okay, so therefore, if it is short circuit, there is some problem with this. So we have to look at always, we have to verify whether all the connections are normal or not. So with this signal, we will get. Okay, click on OK. Then select the accelerometer type. So here we are getting acceleration measurements, and then select the model of accelerometer. This is PCB make. Of course, there are different models. We have to feed the model and its sensitivity here in the software before getting the measurements. Okay. Then click on next. Then click on next. Yes. Next, we have to give input front end settings. Here, preprocessor 1 is spectrum. We have to select preprocessor 2 spectrum and cross spectrum. We have to select. Then click on next. Here, tachometer settings need not give. Click on next. Calibration, of course, done, not required. Click on next. Then we have to give auto range also not required here. Click on next. Here, project measure name. Yeah, whatever name we have given initially, we have to give the measure name. That is demo. With case sensitive, we are giving all the time. You can see project name, sub project name, and measure name. All are giving same with case sensitive, same thing. There is a purpose for this. I'll tell you. Then we have to look at it should be real-time FFT analyzer. It is highlighted and then click on next. You want to give description there in the description box. Otherwise, click on next. So this is very, very important step here. You can see the frequency range of interest here. So like what frequency range you are interested in getting the measurements. Frequency range. Yeah, if you click the drop down list, here there are different frequency ranges which are mentioned. One is like 0 to 10 kilohertz, 0 to 5 kilohertz, 0 to 4 kilohertz. Depends upon, based on the experience you can get. Suppose you are testing a plate, you are testing a beam, small prism, or you are testing like a beam of size 2 meters or 150 mm by 200 mm and so up to what mode we can excite using this impact hammer, that is very important based on the experience. Okay, we are selecting here 0 to 10 kilohertz. It means in this range, let us expecting 3 to 4 modes of vibration. Suppose if you take 0 to 2 kilohertz, hardly you may get 2 modes. So therefore, we have selected, nothing wrong in selecting higher. So suppose up to 0 to 6 kilohertz, you are getting good frequency response measurement. And after that, we can observe some disturbance in the FRF. Of course, nothing wrong. So peaks may not be clear beyond that. Okay, let us select 0 to 10 kilohertz here. Next, click on analysis. Here in the analysis, we have to select window 1 is force, window 2 is response. Okay, here FFT resolutions we have to give, that is 401 or 801. And then we have to adjust these lines to get the visibility of the spectrum. So you can see they are adjusted. Okay, and then go to average. Click on average. So here we have to give click spectral, then linear, mode is linear, and number of averages we were discussing, right? 3 to 5. So to avoid the statistical error in the measurement, okay, we are giving here 3. Click on enter. Okay, and then generator not required. Generator 2 not required. Click on next. Then yeah, arm mode. Click on arm mode. It is select that free run arm mode. Trigger mode. Click on trigger mode tab, which is level. And here we have to select the measurements which we are exporting either manually or automatically, whatever it be, or of course manually we have selected here. Later on also we can change this option. So now trigger mode manual. Now coming to the input level, click the tab on input level. Input level percentage 10 to 15% we have to give. 10 to 15%. And delay in time. Yeah, this is another important parameter we have to look at. Delay in here we'll give minus 0.02. Delay in time. It means, what does it indicates is, indicates when we are hitting the object with the force like hammer, and then we'll get the response from the accelerometer. There is very small delay, like 100th of a second. Okay, so that delay we are giving, so in the minus sign we are giving, it means that the delay won't be there. The moment when we are hitting the object, immediately it will come, response will come. So that is what is the delay. Now here delta level not required, click on OK. Click on OK. Now close all these windows which are appeared. Then go to window, new window. So this is very important step. Here we have to select what are the measurements that we required. We have to select here. First, click on trigger, then click on select channel 1, that is with respect to the force, channel 2, that is with respect to the acceleration, then click on FRFH1, that is channel 2, highlight that, then coherence, click on coherence of channel 2. So these are the measurements we have selected. Now we are keeping all these windows tile horizontal, and then click on OK. Now these are the windows which are appeared. One window will see the force signal, another window will see the response signal which is obtained from the accelerometer, another window will see the coherence function. By looking at that window, we will get an idea of how quality output response we are obtaining for the given input force. In the one more window, we will get the frequency response function. Now we are ready to get the measurements. Okay, now click on run, the top left corner, click on run. Yeah, at the bottom you can see trigger count started here. Now we are at trigger 0, and it is real-time FFT analyzer and trigger 0 at the bottom. So now when we are hitting, that count will change. Okay. Yeah, go there. మీరు ఇక్కడ నుంచి కూర్చొని తెప్పిస్తారా? మీరు ఇక్కడ నుంచి కూర్చొని తెప్పితే ఇక్కడ ఇచ్చింది ఆ షార్ట్ అక్కడ పెట్టి here with us, 3 people we are doing simultaneously. Okay, now we are ready for measurement. So now I click on run. Yeah, now we are hitting at excitation point 1. Here now I got the signal there. You can see here. You can see here. So now I have to accept or straight. Yeah, now I have to accept or reject. What I do is I will accept this. Let me look at see here, force signal has come in the bottom window, top bottom right side, and response from the accelerometer you can see here just above that. And then this is a coherence function, and then yeah, this is coherence, and this is a frequency response function which is obtained. Okay, here we have to look at the coherence. This should be 100%. Here it is 100%. Of course, this is valid measurement. Here you can see at the bottom the count is 1. So first measurement we obtained. So at the same point, the same location, we will hit 2 more times, because we have given, we are taking average of 3 measurements. So now we are going to hit. We are going to hit. Yeah, now hit one more time. Hit one more time. It is a red signal here. short circuit has come. So yeah, here at the red signal is let. So this is indicates overloading of the signal. So we have to avoid that. We have to avoid that. We have to avoid that. Here there is a red light here, you can see. We have to avoid that. Okay. So therefore I discard that measurement. Again we are going to hit. Hit. Again overload. Please hit slowly. Little bit. Yeah, this hitting is also a problem with this impactor. We have to be careful and we have to be patient. Otherwise, yes. Now look at the coherence. Of course, it is 61. Not good. Again, I'll refresh. So coherence is 61%. It has come. Of course, this is 4 signal. Right side top response signal. This is the coherence. This is the FRF. The coherence has come down. There is hitting is not. There is some disturbance. So therefore, now I discard and I refresh. Do it quickly. Let us see. Yeah, coherence is 100% right. Good. Next. Okay. Everything okay. Let us go with this. Again, come down. Okay. Right. So this is how. See, once stop. See, once 3 measurements we got, the count here it is stopped. You can see here. So now we are ready for the another measurement. Now we are going to hit at another location. I hit at node 2. Hit at node 2. Yeah, let me start run. Yeah. Yeah, you can see the response and everything. Response from the force transducer, the bottom right window, and above that, response from the accelerometer. Then coherence and FRF. Okay, I click on accepted. Next. And now the coherence is 95. And now this is good. So like this, we have to repeat at all other excitation points. As I told you, there are total 18 excitation points. Like that, we have to repeat the same procedure. And now I'll tell you the next step. Export of these results. Export of these results. Now to do that, click on, go to file, click on export result settings. Here we have to select the measurements of interest. So that is spec. FR of H1. Double click on channel 2. That is very, very important measurement. We have to select that first. And then coherence. As I mentioned, this is also important parameter. We have to look at. Click on channel 2. Then crossface. We have selected. Now we have selected FRF, crossface, and coherence. Give the file name. I'll give this. Yeah, here look at you look at the names there. Here, whatever name we are giving, project name, sub project name, and measurement name, all are reflecting here as demo. With case sensitive, we have given the same name. There is a purpose for that. Here, give you the file name. So first node we hit it. Now I'll give you a second node. Is node. I have given file name as node. Here we have selected the path where the file is created. Here D drive, GAN in EMA. We have stored all these measurements in that file. Okay, then click OK. Then go to change options. Click on options tab. Okay, then here we will export all the results which are measuring, which are obtaining from force transducer and accelerometer. We will give automatically to export those results. We are giving that option automatic. Click on automatic. Then okay, that file name is shown there and file number is 1. Here, reference and response channels we have to give. Reference channel, component name. Yeah, again another one is come. Project name, sub-project name, measure name, and component name. I am giving same name with case sensitive. So component name is given as demo. Here our reference channel number 11. At 11 we fix the accelerometer. So therefore the channel is given there, and the direction is plus z trans. When we are hitting in the bottom, we have to make our own coordinate directions. Okay, here we are taking this downward z direction, like minus z direction, and upward plus z direction. For response, we are giving plus z. When beam is vibrating, so when it is coming up, this will catch. So therefore, plus z translation we are giving. Coming to this response channel, channel 2, component name again, demo, and the node where we measured, got the measurement, that is node 1. Then click on increment, give the direction, minus z translation. Case of a force, we are hitting downwards, so that's why minus z is given, and click on increment node options. Here we have to click on increment response, then location first. Location step is 1, and here also current location at 1. So these are the settings we have to give here. Then click on OK. Now look at the node list. How we will get the measurements? Where we are taking the reference. Here the reference is at the node number, like excitation point number 11, where we keep the accelerometer, and we are going to hit at all other excitation points, like from 1, 2, 3, 4 up to 18 here. Of course, in that fashion, the results are going to be exported. Then close. Then click on OK. Then click on OK. So now the results are exported. We have to give all these settings for the first measurement. So and then of course we have to export by clicking F9. For the second measurement onwards, simply we have to click on export result, or simply you have to click F9 button. Automatically the results will be exported. You need not give all these settings for each and every measurement. Okay. Now all the results are exported, and that we can see whatever result is exported at the bottom right corner in the screen. You can see that is saved results are exported to as node1.ae2. That is important. So all the results which are obtained, they will be stored in AE2 format, .ae2 format. Of course, this format is not recognized by our model analysis software. We have to convert them from AE2 to UFF format, universal file format, that we are going to do now. Now we have to close this software. Now with this, the basic measurements we obtained from the impact hammer test. Okay, so from the hammer as well as from the accelerometer. Then we are doing conversion of results from AE22 format to UFF format. So for that we opened AE22 to UFF converter, right? So here we have to give the path where our results are stored by clicking File, then load AE2 file, click on OK, then give the path where the results are stored. It is given, then click on OK. Now my result is displayed here, you can see. So that is node 001.AU2, that is retrieved here, right? Now we have to convert this result into UFF format. So now here you can see whatever settings we have given, okay, to get the measurements, everything you can see here. Reference channel, reference location, and direction. Similarly, response channel, response location and its direction, model of impact hammer, model of accelerometer, everything all the settings you can see here in this tab, pop-up tab. Okay, and then click on OK. And now we have to give a path where the results to be stored, converted results to be stored. So now click on change, select the folder where these results are to be stored. So path has been given. Here you can see project name, sub-project name, and measurement name. All are demo. And then we have to give the name of the file which is to be stored in UFF format. That is, let us say mode 1. For node 1, I am giving here correspondingly mode 1. Anything, any name we can give. Any name we can give. I'm giving mode 1. Then click on OK. Then click on convert. So now my first measurement is converted from AE2 to UFF file format. So like this, we have to repeat. We have to get the measurements from all the excitation points what we have selected on the surface of the test object, and after obtaining the measurements from all the excitation points, we have to convert all the results into UFF format. After connecting, getting the data in UFF format, and we can get all the results which are stored in the folder what we have chosen. Now, what we have to do, the frequency response function which is obtained, that is without curve fitting. Now we have to do curve fitting of that using another software which is NV Solutions model analysis software. We are opening that now. Okay, so this is now we have opened another software which is called NV Solutions model analysis software. Now we are closing VARA software. Okay, here we have to create our project file. Click on file and then open a new project. Click on no. Yeah, your project is created. Okay, so now we have to create the geometry. Okay, so this geometry will be created based on the excitation points what we have selected. Now click on analysis, go to geometric wizard, click on that, then click on next, geometry wizard data source, therefore click on next. So now here geometry wizard component definition. Yeah, this is very important step. As I mentioning, component name. See, initially project name, sub-project name, measurement name, component name, geometry name. Better all these things should be given same name with case sensitive. So otherwise this software won't recognize for the measurements are for which it is. So therefore, so we have to give same name here for this. Okay, don't think that for any type of analyzer or any type of what we have to give like that. Whatever we are having for this, we have to do that. Okay, so now we have given the same name, geometry also. Click on next. Now we have to create the geometry by giving the coordinates. We have to downward we have taken as like Z translation, and in the lengthwise we are giving X. Okay, breadthwise we are giving Y. Now all the node excitation point numbers are giving here 1, 2, 3, 4, 5, 6 up to 18. Now coordinates, after that we have to give coordinates of those excitation points by selecting one of the points as reference point 0, 0, 0. Now excitation point 2 along x direction, let us say it is 50 centimeter beam, means each 5 centimeter, each 10 centimeter we have selected one excitation point. Then in x direction 10, 0, 0. Next point will be at 20, 0, 0. Then, yeah, y direction. Yeah, y direction, that is selecting in length direction. Okay, breadth direction is x. So any sort, but you have to be consistent with that. Okay, nothing wrong. Any fashion you can select. Okay, 0, 10, 0, 0, 20, 0, 0, 30, 0. Like that, only y dimension is going to increase up to 6 points. Later on, see, 7th point will be y is 0, x is there, 5, 5, 0, 0, 5, 0, 0, 5, 10, 0, next. Like that. It's a simple geometry only. Take your pen, otherwise if you are confusing, take the pen, paper, and first of all draw the geometry and give the coordinate. Same thing you can type in the software. You are still confusing. Okay. Right. So now my coordinates are ready. So and then click on next. Zoom it, press shift and yeah. Now these are the okay, right. Now these are my excitation points. Now we have to join all these coordinates which are created. Click on each point. Yeah. Point 1, point 2, point 2, point 3. Like that, do it. Middle. One, two. Click on one. Screen. Yeah, here we are creating the geometry. Highlight 2, 8. 2, 8. We have the next. 8, 14. Then 3, 9. 10. 4, 18. So this is simple thing. You can easily do that. Either enter the coordinates to be connected in the table, or with cursor also you can do. Okay. Now click on next. Now this is my test surface. 7 and 8, 8, 9, 9, 10, 10, 11. Yeah, now this is, you can see the entire surface, test surface, from where we got the excitation points. Similarly, we have to create here the geometry. Okay, whatever points you have selected, those things should be created in the software. Yeah, you can see the rotation, everything, what I, with respect to X, Y, Z, you can do the rotation, everything. That all those options are there. Yeah. Now click on next. So here we have to give the name of this geometry, same demo we are giving. All these things should be consistent. The names. Click on next. Okay. Now, this is my geometry which is created in the project. What we created, you can see. Click on right click, different options, node numbers you can give, and undeformed shape. There are different options. Okay. While vibrating, while getting the mode shapes, frames per second, how many frames should be there, all these things we can select here. Okay. Therefore, now what we are going to do is close this. We have to feed the measurements what we obtained. Our measurements we obtained. Now here, the measurements, whatever we obtained, we have to load here. Load those. So like all the measurements, by hitting at all the excitation points, whatever measurements we obtained, we converted them into UFF format, and those measurements are dumped into the project what we have created in model analysis software. Now we are ready with all the measurements. You can see they are loaded. See, for all the 18 points, see, you can see measurements like frequency response function, that is very important. So all those are obtained and dropped in the project which is created here. Below those measurements, you can see there is a geometry, the red color, and also you can see the response. Suppose if you take any measurements, where the response is, where the reference is, all these things you can look at in this window. Okay, now we are ready for the analysis. What we do is, we'll click on analysis, click on SDOF wizard. Yeah, click on next. So here we have to select measurement direction in which we measure the force and response, that is in Z direction. We have given plus Z translation minus Z translation, right? While exporting the results. Therefore, we have given that. Click on next. Now this is the curve fitted frequency response function. See, total how many frequency response function we will get? There are total 18 excitation points. At one excitation point, we fix the accelerometer. Therefore, between one input and one output, one frequency response function will come. Okay, sir, one FRF will come now. Anyhow, natural frequency won't change for the given structure or a member, whatever it may be. Why we have to get the measurements at all the points, what we have to select it is to get the mode shapes. Otherwise, you won't get mode shape, but you will get nasal frequency. See, this is driving point FRF. That FRF, it is driving point. Yeah, 11. Yeah, this is driving point FRF. You can select the which FRF to be displayed. Yeah, click on OK. So now the frequency response function we obtained. You can see the mode shapes. Yeah, peaks you can see. We can shift that cursor. Yeah, this is the first mode of vibration. Keep it. And fine tune we can do with the bringing that red cursor, analyzer cursor near the peak. You click on peak, that will give you the exact location of the peak, and you can see how the first mode of vibration. Right click on that, give undeformed shape and frames per second, and that all the displays, graphic displays in that pop-up window. You can do click on undeformed shape. Okay. Yeah. So now the equilibrium position you can see, the first mode of vibration you can see, the top right corner you can see what is the frequency in the first mode, that is 1562 Hz. Okay, here the damping is 0.96% and the curve fitting method here is finite difference. There is one more method in this software, which is quadrature method, which was discussed in the morning, quadrature picking method by Professor Mantana. Okay, now shift the analyzer cursor to another location, another peak. Yeah, this is the first torsional mode you can see. See, in addition to the bending, torsional modes have also come. This is the first twisting mode. You can see how it is twisting. Okay, can fine tune that. This is first twisting mode. So this is obtaining at a frequency of 2510 Hz, 2.5 kilohertz, and the damping at this location is 0.5. Next, so next peak. Yeah, this is the second flexural vibration mode. You can see here, second mode of vibration. So with the shape itself, we can identify that it is a second mode of vibration. Okay, so the frequency of this second mode of vibration is 3660 Hz, and the damping is 0.46%, and that is method used is finite difference. Next, go to next peak. Yeah, one more important point. See, peak in between there is a anti-peak. You can see downward. Yeah, that is anti-peak. In the driving point FRF, those anti-peaks we can observe. Also, peaks are very sharp. Okay, narrow. So with the looking at that, we can see the FRF is a driving point FRF. What is the driving point FRF? The point where we give the input force and we measure the acceleration response. Okay. Now this is third flexural mode. You can see here. Third flexural mode, frequency of corresponding to this peak is 6128 Hz. Damping is 0.44%. After that, yeah, slowly also we can give. Slowly we can see here quickly. Those amplitude of display also we can change. These are all graphic displays. Okay, for scale displays. Go to next peak. Next peak. See, you can look at the FRF here. Beyond that third flexural mode, the FRF peaks are not clear. So it means there was some disturbance. So for this beam, this is just a concrete prism which is so stiff. Okay, so we could not be able to get proper modes beyond 6 kilohertz. After that, there is disturbance. Keep next peak. What happens? We'll see. Okay, some sort of torsional mode. This is, but flexure and torsion combined. Next one. Go to next peak. Yeah, these peaks are not clear. There is some noise or disturbance you can observe here. So therefore, up to 3 flexural modes could be able to excite with this using impact hammer on this test wave. Okay, we can also store these modes. Therefore, there is a store option here. Suppose I am at node 3. I click on the store. Here you can give title mode 3. Okay, the entire description is given there. What is the natural frequency in H? What is the damping? And what is which method it is used? Everything automatically it will come. Click on OK. That will be stored. Again, go to second mode. Store that. Click on store. Give mode 2. Next. Same fashion, we have to store whatever measurements we obtained. Okay, all the measurements modes you can store here. Yeah, next. Store mode 3, then mode 2. then mode 1 flexural mode. Okay, all these are all stored. Show those. The results we can see. Click on next. Yeah, these are the results what we stored. Okay, so first mode of vibration, second mode of vibration, third mode of vibration, and then click on save. Those modes are displayed in the project what we have created. You can see here, left side you can see measurements which are obtained from the analyzer, geometry which is created here, and then the modes which are stored here. And also we can look at how the FRFs are look like at all the points you can see. And do the analysis. Select all the FRF points. At one point, go to data. Select all FRFs. If superpose, if you look at, see whatever input and output, suppose output response is fixed. You are giving input at different, hitting at different locations. You will get one FRF for each case. If you look at, you see this is the plot. All the frequency response functions, total 18 FRFs we obtained, all are superposed here. The peak should be coincide. See, it means the natural frequency of the given object won't change, right? So therefore, you overlap all the FRFs, you can see the window with each FRF with having a different color. You can see all the FRFs are overlapped here. My advice is, of course, you can get this plot, but to get good, to identify good peaks and then modes of vibration, better select a driving point FRF and get and measure the and obtain the dynamic characteristics in that curve fitted frequency response function. Okay, so with this we completely obtained the model parameters or dynamic characteristics using this impact hammer. Okay, so any doubts or any clarification in this, anything? Once again, you just look at the setup and everything. Okay, everything like some hammer, analyzer, then analyzer, then go to the test field. Okay, you can see there accelerometer, impact hammer, setup connections from accelerometer to impact hammer to the channels of analyzer, from the analyzer to the data logger to the PCMSI slot. You can see there. Of course, this is PCMSI. World interface is this. Nowadays with USB interface, analyzers are coming. Okay, this is what about the impact hammer testing. You can carry out same test using different like boundary conditions, different types of materials. You can test the composite. You can use composite coupons in like cantilever boundary conditions. Boundary condition, whatever we wish, we can create. Okay, you can repeat the same test for different types of materials, different types of members. Okay, only thing is you have to have some basic idea how the mode shape would be so that you can select the appropriate location of accelerometer. Why that is very important, because if you keep the accelerometer at one of the nodal points, node of a mode, so you cannot get the measurement. That is the only thing you have to get. This is a very simple experiment. We can carry out good research on this using this by identifying the dynamic characteristics, and in the laboratory also you can identify, you can see by introducing some damage. Suppose if I introduce cut to this concrete specimen somewhere, again I repeat the same procedure. What happens to these dynamic characteristics, you can verify what happens. Again increase the level of damage by increase the depth of the cut. Again what happened, you can correlate the extent of damage and change in model parameters like that. So that will give you some useful information the extent of damage, uh, how much it is based on the percentage variation in the dynamic characteristics. Yeah, any clarifications, anything with respect to
Good, sir.
damage? Yeah, yeah. Please identify yourself first and then.
My name is Jayakumar.
Yeah.
Yeah, am I audible, sir?
Yeah, yeah.
So, which method is the best for model analysis? Either we can use peak amplitude or circle fit method.
See, that representing the FRF, there are different ways of representing that.
Yes,
Okay.
sir.
So here in this software, it is like a quadrature pick method it is used. There is finite difference method, one more. Okay.
Sir,
These are all single degree freedom system curve fitting techniques. For FRF display, there are different ways of displaying them. Morning we have seen. Okay. Professor Manthana highlighted all those things. Right?
sir, you have simply shown the FFT in the software.
Yeah.
Sir, so I want to ask you about the power spectrum density. There is some difference between the FFT or power spectrum density?
Power spectrum and cross spectrum, of course, there are measurements.
Yes, sir.
Okay, cross spectrum is like between like input output. We are giving input at one location and getting output at other location. So these are all there. But background mathematics theory, of course, they are based on with DSP, digital signal processing. Okay, so background, what is happening like windowing, okay, power spectrum, cross spectrum, okay, and force window, exponential window, what are the mathematical expressions involved there? See, these are all, of course, there are fixed mathematical procedure for that. Okay, so of course, morning we have seen all those expressions, but they are a bit boring. That's why without much of mathematics. Okay, so in the last we have seen the procedure which is given by Peter Revitable, and now okay, this is the demo based on that. Okay.
Sir, you will also perform a test multi-point excitation and multi-point measurement in the
That
next.
is okay. Like multi-point input and multi-point output, right?
Yes, sir.
Yeah, that is not that facility. Of course, we have 8-channel analyzer, but we can do that, but that is not done. Okay, we can try that. We can try. The accelerometer also, this is uniaxial accelerometer. You can
Yes,
use triaxial accelerometer also to get response in 3 different directions.
Yes, sir. And my next question, sir, is the accelerometer is the best or a laser vibrometer is the good for the measurement?
Yeah, everyone, I think it has its own advantages and disadvantages. Of course, these are more proven. These piezoelectric sensors are more proven. We can get good measurements. Yeah, of course, the laser vibrometer also non-contact type. We can also get yeah, that is the only difference.
Okay, sir. Thank you, sir.
Sir, good afternoon, sir.
Yes.
Sir, myself Rudra Amarnath Babu, sir.
Yeah, yeah.
Sir, the practical thing was very good, sir. As if we feel that we are doing, but only thing is the resolution of the computer itself. Okay, sir, that's not an issue. We can understand, sir.
Yeah.
Sir, I got three
Now this
questions,
is
sir.
this is very old one equipment, and that interface nowadays with modern laptop that we don't have. So therefore we are
Okay, sir,
using
no, sir.
keeping that preserving that laptop because otherwise this equipment won't work. So that screen.
Okay, sir. Okay.
Okay.
Sir, sir.
Yeah.
Sir, the first thing is, sir, the number of modes of measurements, what you said about the coordinate axis, sir. You
Yeah.
said that Z will be taken as a minus Z coordinate.
Yeah.
Sir, we see once for the first point, if you follow the same coordinates, is it necessary to follow the same coordinates for all the points, sir?
Yes, yes, same. See, first of all, you have to identify while fixing up the excitation points, like along the length. Suppose if you take this beam along the length, okay, whether I have to give x direction, y direction, or z perpendicular to them, other coordinate directions. Anything you can select, but consistency should be maintained till the creation of the geometry.
Okay, sir. Okay, sir. Okay, sir.
That is the only
And
thing.
sir, and okay, sir. That is the second point is regarding the shape of the specimen, sir. What we select, say, see in the practical, you have shown the cubic rectangular one.
Yeah.
if the shape of the specimen changes, the methodology also changes, sir, or is the same thing to be followed?
Methodology is same. Methodology is
Same.
same.
Okay,
Same,
sir.
nothing will change. But only thing is, you have to create that model, which should resemblance the actual one. That is the only thing you have to look
Okay,
at.
sir. Okay, sir. Okay, sir. Okay, sir. Sir, is it apply also for the composite structure, sir?
Same, sir. Same. Yeah, you can do that.
Okay, sir.
Same,
Okay.
yes.
Okay, sir.
Same
Thank you,
thing,
sir.
same procedure you can repeat using any type of composite,
Okay.
any different sizes also.
Okay, sir. Okay, sir.
Good afternoon, sir. This is
Yes.
Dr. Venkat from Gayatri Engineering College, Visakhapatnam.
Yeah, good afternoon, sir.
Sir, how many modes will go for from the model analysis?
See, for to get the like behavior of any structure as it was highlighted, lower modes are a bit dangerous. So to get the observation, to get behavior of any structure, so it is important to get the lower modes of vibration. But here, how many number of modes we will acquire? That is based on like the test object, based on the type of hammer and its weight. How many modes we could be able to excite in the given frequency band. So we have to have some idea. Suppose based on experience, what we have seen is for this size, okay, so we could be able to excite up to 3 modes, okay, up to 6 kilohertz. So that's why we have given the range 0 to 10 kilohertz in the settings. So beyond 6 kilohertz, there was some disturbance in the FRF. We can see that clearly. So,
That means if
by
I have
carrying out a couple of experiments, you will come to know. Suppose earlier when I was started with the experiment, I have given only 0 to 2 kilohertz. Okay, so that the beam size is different. So in that 0 to 2 kilohertz, I could be able to get 3 modes of vibration. Okay, this
Suppose
is
if
so
I have,
stiff on. Yeah.
if I have a cantilever beam, it will be flexible, so I can go for more. I mean, I can extract more number of modes.
Yes, yes, yes.
One more
But
thing, sir.
while looking at the free FRF, you will come to know, yeah, whether the modes, whatever we are acquiring, they are good or not. So is there any disturbance? Later on, the next, suppose if beyond 6 kilohertz, the FRF is not look good. So therefore, next time while I am carrying out, I can give the range will be 0 to 6 kilohertz, so that the good FRF we can look at with distinct peaks.
Okay, sir. So one more question, sir. This
Yeah.
suppose the extracting, doing the mode analysis, that's mode shape and frequencies.
Yeah.
Will it be good using the impact hammer, or can we can get the good mode analysis using the shaker, which is better, and which
See, yep, concept wise it is same. Only here we will move the hammer here, roving hammer. There roving accelerometer. Roving accelerometer. That we have to see.
No,
Keeping like see some type of like systems. We have to induce the vibration. We can induce vibration only in terms of using shaker only. Okay, so therefore such situations we have to use that. But here for our civil engineering laboratory specimens, we can use this roving hammer. This would be fine. This works well. Based on the case to case.
Yeah, if I want to construct a 3-story building model,
yeah,
with a and then a small 300 by 300 size.
Yeah.
So then, I mean, to get the proper modes, I will be good to have a shaker or an impact hammer will do their work.
Yeah, so of course you can also use hammer, but this small hammer doesn't work. Depends upon the size of the body. Size of the body, we can use large sludge hammers, even small culverts, bridges also we can test. We can excite using those sludge hammers with larger size. And of course, accelerometers also, they are different. We can carry out, we can use both.
Okay.
Only thing is, we have to look at with the hammer, with this particular hammer, we could be able to excite or not. If at all, how many modes we could excite, these things we have to look at. We have to observe first, think of first.
Okay, sir. Thank you, sir.
Any other?
Good afternoon, sir.
Yes.
Sir, does the peaks indicates the mode number, sir?
Peak indicates the resonant condition.
Okay. How can we find the modes from the peak, sir?
Yeah,
different
that
type of modes.
when you are bringing the analyze cursor there,
Okay.
so you can see the right side window, the modes are changing. So by identifying that pattern of vibration, we can say that, yeah, this is the first mode. Some basic knowledge already everybody, I think, might have studied structural dynamics or machine
Yes.
vibrations, right? Based on the for the given boundary conditions, how the mode look like. So based on that, we can identify, yeah, this is the first mode of vibration, this is second mode of vibration, like that. We have to identify that.
So, sir, in that modes we have all the bending modes and torsional modes.
Torsional
No,
mode.
sir?
Yes, yes. In the
How
FRF,
can we define that this mode belongs to bending
yeah,
mode and
that's what I am mentioning. Suppose keep the cursor at first mode, first flexural mode. Yeah, this we know for a simply supported beam. This is the flexural mode. See, it is vibrating. That we know without any distortion.
Okay.
Okay. Now go to first peak of torsion mode. Yeah, this is twisting. You can see this is the first torsional mode. In fact, this we are getting at second peak.
With the help of the mode shape only, we can analyze whether it is a bending mode or torsional mode.
Torsional mode, yeah. This is first torsional mode, but we are getting this at second peak. Don't think that at second peak, second mode of vibration, we'll get second flexural mode. Okay, this is first torsion. If you go keep analyzer cursor at third peak, second bending mode will get.
Sir, if we consider a cantilever beam,
yeah,
if we do the FFT analyzer,
yeah,
does that first peak for the when I consider the bending mode,
yeah,
for the first mode for the peak of the peak will be more or lesser. How can we determine that?
See, by looking at the mode shape only, we can identify that. By looking at the peak, we cannot say, we cannot judge anything. Okay, whether it is torsion mode or bending mode. So suppose there is a distortion in the first peak, let us say, then that is first torsional mode. Like that, whether that frequency can be less or more.
Sir, if there is any damage or deterioration in the structure,
yeah,
then we can observe the shift in the frequency spectrum.
Yeah, shift in those peaks. Yeah, what we can do is give some damage in the, you put some cut somewhere in the beam. If you repeat the same procedure and you overlap both the FRFs, that option is there. You superpose both undamaged condition FRF and damaged condition FRF. So we can observe the shift in the frequency, in which direction it is shifting. So it should be, of course, peak should be shift towards left. Yeah,
towards left,
because stiffness is decreasing, right?
Yes,
so
sir.
that we can observe by superposing both the FRFs.
Thank you, sir.
Sir, continuing to his question, this peaks corresponds to eigen frequencies, right, sir?
Yes, correct.
They are in the increasing order.
Yeah.
Okay.
Yes, any other?
Good afternoon, sir. I am Neeraj Yadav.
Yeah, Neeraj.
DRDO. My question is like here we did in the vertical direction. If we'll do impact hammer in the horizontal direction, then we will get some first, second, third mode frequency. So how they are? So if in practical,
there are three ways. Suppose if you look at ASTM code, of course, to measure some basic dynamic parameters, there are three. See, you can get the longitudinal response. Suppose like in horizontal direction, if you would like to hit. So in that case, what I do is I'll hit in horizontal direction and I place the accelerometer against to that.
Yes, sir.
The longitudinal vibration. That response also we can get. There are three different ways. Either for torsion like vibration we can monitor by keeping accelerometer at one corner and hitting at other corner. Okay, there is a specific ASTM code for this. The number I did not remember, but how to carry out that ASTM C515 215 something. ASTM C215. So boundary conditions how to create for longitudinal waves, transfer waves, and torsional waves. Everything is mentioned. So from that we can get you can carry out the behavior.
To avoid resonance, should we consider both frequencies or vertically sufficient or horizontal sufficient?
Yeah, but normally we will look at transverse vibrations only. But me people, maybe mechanical people, they will look at torsional modes also.
Okay, sir.
Yes. Okay. Otherwise, now there are no questions. We will stop here, and we are closing today's session. Tomorrow we will resume our sessions at 8 a.m. and most of the people not turned up at 8 a.m. I am requesting you because all lectures are very, very important. So therefore, my advice is to be available at 8 a.m. sharp. People are slowly joining up to 9. Maybe, of course, you may are busy with some other things. So it's my advice. Okay.
So one more question is also
Yeah.
there. Like in our impact hammer test, we got our first frequency 20 hertz.
Yeah.
So how much plus minus should be my means the real frequency to avoid the resonance? Like how much far it should be?
Yeah, then we have to make some comparison. Like can do some numerical simulation. Same thing. You can create the model. You can use ANSYS software. Yeah.
I'm asking there is some standardization like plus minus 5% should be there, like 10% like that.
Some generally, how much percentage change in peak like peak frequency? Not damage for any measurement, whether it is correct one or not, to verify repeatability. That's why to avoid that only we are giving that this one averaging function.
No, we will get the first frequency like 20 hertz. But in practical situation, if my equipment is working on 19 hertz or 21 hertz, so how much far it should be from the natural
How
frequency?
much percentage deviation? Okay, should be something like
Yes,
that.
sir.
The actual operational frequency and this one measured one.
Yeah.
That should be to observe the behavior should be as close, but percentage deviation. Suppose machine is working at some frequency, which is measured.
Which is measured. Okay. Yeah. So we are here. What we are assuming is that the system is measuring exactly what the frequency
At which it is working.
at which it is operating.
Operating.
So is your question
that
whether the equipment is working at slightly different, is operating at a different frequency from what is supposed to be ideal? Is that
Yes, sir.
Yeah, that yeah, that is
Like
what we have to do now in this.
Like if it is some nearby to our natural frequency, then we'll do something change so that it should be far from that.
No, no,
So
no,
how
no.
much far?
Let us be clear in the question. We are not understanding the question. That's why we are asking this repeatedly.
Like in that measurement, we get 20 hertz, our natural frequency, first frequency, and our machine is working at 18 frequency. So is it safe for the
Safe
resonance?
only.
So
Oh,
if it is
so
working
you are saying
19.5,
resonant frequency is 20 hertz.
yes, sir.
Resonant is 20 hertz. You are
Yeah,
like
then it's
safe only, no?
So I'm asking that how far should it be? Like if it is working 19, is it safe? It is working in 19.5, is it safe?
Here, see, there are several factors. It is not very simple because first of all, you have to look into when you look at the FRF of that particular piece of equipment and its response. Let us say, okay, if the FRF is if the peaks are very distributed, that is, if they are very shallow, the slope is low, which means the damping is high, right? The quality factor is also low.
Yes,
It
sir.
means there is a lot of internal damping in the system, and the response goes slowly to the peak. Okay.
Okay.
Right. It is this peak versus this peak we are talking
Yes,
about.
sir. Yes, sir.
Okay. So if it is like this, then you have lot of well, very close, even up to say It depends on the quality factor. It depends on the sharpness of the peak.
Okay, sir.
Okay? Because if it is a peak like this, you can go very close and only
Yes,
then
sir,
it
very
will
early.
start to resonate. Whereas if it is like this, you will start getting increasing amplitudes from quite a more than plus or minus 5%.
Yes, sir. Yes, sir.
So it depends on the damping in the system.
Okay, sir.
Anything? Okay, let us.
Sir, I would like to add
Yeah.
to that. Like
Rajesh.
when resonant frequency is 20 hertz, he asked it what frequency we can run it. So during my lectures with Bangar Babu sir, he was mentioning like 70% to the left and right is a safe zone. Like,
See, anything which is closer to the resonant frequency, which is undesirable,
yeah,
right?
correct.
It is undesirable. So we should be as far as possible. That's it.
Correct. Yes, sir.
See, normally for any machine or anything, up to 70 to 80%, it is a safe zone for anything.
Mm.
If we take any machine in our laboratory, what we are working with, suppose if we take a UTM, which is 100 tons capacity, it is advisable to apply 80% of the load while testing. Yeah, that's it. See, so normal up to 80% would be the safe zone. Okay, for any
But
machine
sir, it is not
or
possible.
working with for anything. Yeah.
Okay, sir. Thank
Like
you.
if there are so many rotating things now, so close of frequencies are there.
Yeah. So that is the thing. So that's why we have to keep dampers to minimize that response. Base isolators, dampers, all these things come into picture.
If the equipment is already there, so we cannot
Yeah,
change.
that's why. That's what. See, we have to use some sort of isolation system. That vibration should not transfer from one component to another component. So some sort of mechanism we have to do to avoid that resonant condition. To minimize the response at least. So you cannot avoid the resonant condition. That is the only solution. See, all the structures are built, machine is already manufactured and it is in working. Cannot avoid the resonant condition means we have to look for some other alternatives like using dampers, base isolators.
No,
Okay,
if we
while
are designing, then we can
creating
change.
foundation to that, use some sort of isolation system.
Like I was doing the model testing on the helicopter.
Yeah.
And we have to mount some equipment on that.
Yes.
So if our extra equipment we are implementing there, so their frequency also matter. It should not match.
We can alter the frequency. It means the frequency of the object can be altered by keeping some extra mass somewhere, like that.
Yes,
without affecting its performance. That we can do.
Yes, sir.
Of course, we can cannot introduce cut or remove the like some portion, but adding something, okay, without affecting the performance, we can do.
Yes, sir.
Okay. Anything else? Okay, right. I am closing down. Again, we'll meet tomorrow morning at 8 a.m. Tomorrow, Professor Mantana start off, and afternoon experimental session. Okay, we'll see. We are trying to show you other type of system. Okay. Thank you one and all for your patient listening.
Thank you so much.
Thank
sir.
you.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Sir.